The Tiger Beetle sessions, Friday, 14th January, session 8. Hey, Isaac, what's up?
Hey, Aaron. Welcome back, everybody. I guess when we left off yesterday, we were finishing up the right path for our in-memory manifestation or manifest implementation, not manifestation.
Uh, have you been playing
That's a,
StarCraft lately?
I don't know. I have not. It's just like, I guess that's just an interesting audio typo that can happen. Um, So, for the right path, we've now, well, I guess we can just pull up the code real quick so we can like have something to look at. This level manifest, or no, manifest level is what we called it. Um, or the read path is what I'm talking about too, not the right path. I have just misspoken every word I've said today the same. But we've kind of got two steps here. The tricky part is finding out where to start our iteration. Once we like find the table info we want to start iterating at, it's pretty simple. We got a pretty simple iterator in the segmented array abstraction. Here our iterator just always goes to the next thing and then goes to the end of the array. The tricky part is finding where to start this iteration efficiently. Because it would be easy to just scan until you find the right place to start from the beginning. Just do a linear scan, but that'd be slow, of course. And so instead we do a kind of tiered binary search here. First searching on the root node, and then, if necessary, on inside the key nodes, in order to find the place to start iteration. But there's a subtle issue with this because we can have table infos with the same key but different snapshots, such that they are not actually visible at the same time, but they're still stored in the same array with the same key. So the binary search won't give us the exact one we want. It'll only place us in the cluster of table infos with the same minimum key. And so we then need to do a slight correction where we iterate for just a few iterations possibly, or maybe even 0 iterations in the wrong direction to like get to the edge of the cluster of matching keys, min keys we want to start at. And so that's
Yeah,
what it's just started implementing, or I think actually implemented now
yeah,
here at the end of the last. Now I think our first task is to refactor this, add some assertions, and move it to a different place in the code probably, because we want to put it inside the iterator start method, so we abstract away the whole startup method cleanly.
yeah. Did you see that
Did I
clip
cover
that
it
I,
all?
yeah, perfect, awesome. Did you see that clip that I did from yesterday's session where we came up with this, go backward to go forwards, go left to
I
go
did not
right?
yet.
Okay, okay.
It's a good
That's
one to
pretty,
clip though.
yeah, it's pretty cool. It's just a 1 minute clip on Twitch, and it's a great way to like see how we arrived at the solution. Um, yeah. So
Cool.
basically we've got this array of table metadata. Each table info in there has got a min key and a max key. So we've got all these tables in sorted order by min key. The problem is that you've got also we've got to hold on to references of deleted tables because of snapshots that can still see them. So to do snapshot isolation, like a form of read transaction, we've got to hold on to all these old deleted tables, um, and that's what makes this binary search complicated. Because, like Isaac said, we binary searching, but you could have multiple tables with the same key. Some of them we can see, some of them we can't see. So we've got to do this little correction, fix it up, and it was getting really complicated yesterday. And then Isaac had this killer idea, like, let's just go iterate in the wrong direction. And then we turn around and come back. So that clip was pretty fun.
Yeah,
Um,
this handles all the edge cases really.
yeah, and super
Because the binary
simple.
search is guaranteed to get us to the right min key to start at, but what makes this then hard is that there's multiple things with the same min key. So we just need to make sure we then adjust to the either the first or table info with that min key or the last table info with that min key, depending on the direction we're iterating.
Yeah,
And so we always see all of them during iteration.
yeah,
And during this adjustment, we don't actually like return the table infos from our iterator, of course. We're just kind of adjusting the start point of our iterator, which then does all the balance checks it needs to and checks against the snapshot range to
yeah.
see if the thing's actually visible to the current snapshot or to the provided snapshot. tick, I think we're calling it now.
Yeah. Yeah. Awesome.
Cool. And so that's what this code does essentially. We just take the reverse iterator. We add this nice direction.reverse function to give us the backwards direction for whatever direction we're looking at. And we like stash the position of the exact thing we got out of iterator start, and assert this is the same as the first thing that will be returned from the reverse iterator. Then we find that we get the start key by calling reverse.next once. We can always do this because we always know that these that the relative index and key node returned by start will always be in bounds. Otherwise, start or iterator start will return null. And that's only in the case where there's no items in the level manifest. That's the only time we return null there. And then here, we get the start key. We're now iterating over the keys. We're iterating over level.keys, not level.tables. So we only look at the min keys of each table, which will be faster than iterating over the tables. It's just less memory to access, and the nodes have more keys per node. But we don't expect to iterate very far, so it probably won't matter very much. We'll only be iterating a few entries in the normal case, because there won't be that many snapshots, we believe. And depends on the use case, though, because we do support like arbitrary numbers of snapshots now, I believe. There's no bookkeeping overhead is not very high. It's just like a couple integers written to disk to say that these snapshots exist.
Yeah, we'll still have a limit on the number of snapshots, but it'll be high, like maybe 64 or something like that.
Yeah, that makes sense. And so so we've got then currently the start or adjusted now is the index and relative index and key node of the first element returned from the start key. Then we set next adjusted to key, which will be returned from reverse.next. So to this k, and then if we check if this k is actually outside the range we want to look at. If it is, we're done, and we are then just use adjusted. If it's not outside the range, we do want to look at the next k, and we'll set adjusted to next adjusted, which is the index and key node of k here. And then we'll adjust or take next adjusted to set that to the next key node that will be returned here. And we need this two-step kind of process because next increments the relative index and key node for the next iteration on calling it before it returns. Yeah. That's a good summary.
Yeah.
I think we were considering a couple things to make this better last time. One was to put the key node and relative index in a struct and use that in next as well. I have like I don't know what to call it. Do you have a good name for that?
It's kind of like a position or an offset, because the tuple gives you the actual offset. Maybe it's an offset, like the node plus the relative index gives you the index. Index or offset.
I feel like the offset is just the relative index though. It's kind of like I feel like it's more like a position or.
Yeah, because it takes into account the key node. So basically we're going through the segmented array. So if you know the node and the relative index, then you have the absolute index, those two together.
Yeah, and so they're equivalent to the absolute index, right?
Yeah.
But the reason we store them in this layout is because it's just like faster to use. We don't need to then derive the. Yeah. These are the things we use to actually access the data. So it's like totally cheap in O1 to go from these two indexes to the table info that we're referring to.
Yeah.
Whereas if we store the absolute index, it wouldn't be as cheap, though it'd still be fairly cheap because we've done some optimizations there.
Yeah.
We didn't need to do some iteration in that case, potentially.
So these are the two components of the absolute index, but we don't we don't decompose them into a single number. We preserve the information because that way we can just bump the keynode to jump across keynodes quicker.
I think I want to call it position. What do you think of that?
Yeah,
Cool. I think you should also go inside segmented array, perhaps.
yeah, I think so
That's
too.
like where the things come from.
Yeah,
Cool. So I guess this will be just part of the iterator struct. We just kind of call it like iterator.position even.
yeah.
These two just go in there. Now we need to adjust all these things though. So we're gonna add now a bit more verbosity here, which is not ideal.
We could, yeah, position. Yeah,
Position
because you don't
pause.
you don't want to say iterator dot index dot relative index. That doesn't make sense. So
Nah,
position, offset
you
is a
pro
little bit shorter than position.
I feel like it's not accurate though, because
Yeah,
offsets are always relative, right? Um, well, or I feel like I usually think of offsets as being like possibly relative.
yeah, okay.
You also just
Then
call the struct field pos instead of position if you're happy with that. Makes this a
yeah,
bit less verbose.
yeah. I think we should do a full like keep to our thing where we keep use a full name.
Yeah, I was thinking you would say that.
Yeah, yeah. Okay, but I don't mind it like if this still looks good. How's our line length on line 3, Isaac? Cool.
Yeah, that's 87 only.
Mm,
Remember the font size is pretty big,
yeah,
so that's actually fine.
yeah.
We need to do it for the other one too. I think it.node is what it was. Yeah,
Another
it.node. Dope.
another name that's shorter and 2 syllables is cursor.
Okay, that's also good. Yeah, I
Yeah,
like that a lot actually, because that's more. Yeah, and then we have position at relative index can become cursor dot relative index. Oops, not that. And then here we just make this cursor as well. I think that's better.
cool.
Because that's also like this sliding thing we use during
Yeah,
iteration.
yeah.
And so, yeah.
And a cursor often has
Um,
more than one component, like it has a row and a column. Yeah.
yeah, cool. And then I think I'll just do this bit here, like that.
Nice. It's also
Okay.
nice to put them together like that because you can see what relative index means, that it relates to the node.
Indeed, yeah. And so the question would be like relative index to what? Now it's pretty clear.
Yeah,
Um,
yeah, exactly.
we could even maybe drop the relative prefix. I'm not sure.
I was just suggesting, I was just thinking of that. I thought maybe you wouldn't want to, but
Yeah.
yeah,
Or if we
maybe,
said node and offset. I think it's then pretty clear it's an offset like from inside the node. I don't know. Like relative index is still like the more, it's super obvious what it means right now. If we
yeah, yeah,
change it, it's gonna make it less obvious. So I think we just leave it probably.
yeah. I think it's. I,
Um,
I thought so too. And then also it matches nicely with our absolute index outside.
Indeed, yeah.
Yeah,
Cool. So that's now done up nicely. Now here we need to switch to returning like a I don't know tables dot iterator dot cursor type. Oh, so this is gonna be interesting. So now I've made it part inside the generic, which is not ideal. Because
Yeah.
now you can't find the keys one to the tables one. So let's move that out. Actually,
Okay.
we don't want this doesn't need to be inside here.
Yeah.
Um, yeah, this can just go, I guess, up here,
Yeah.
and then we'll import that as well. Whoops. Um,
Shall we call it a segmented array cursor as the type?
we can call that. A little bit longer, but I think it's fine. We don't actually type the type any or very often, I don't think.
Yeah.
I think we'll only actually type it once in the array type in the return
What?
type.
Yeah. What if
Um,
we don't want to put it in the segmented array type itself because then then we've got that's
because then it
generic.
depends on this type T, even though it doesn't need to.
Exactly. Yeah.
Um,
Okay. Cool. Nice. We might need to just update the
okay.
references inside segmented array. I think we still have some cursor references.
Yeah, you're right. It's just that one place, I think.
Yeah.
Yep, just that one. Cool. And this is all also good now. So now we can clean up this code a little bit and just say adjusted equals start, and then say um, next adjusted equals reverse
River.
cursor.
Yeah.
And get rid of those bits, and then adjusted equals next adjusted equals reverse dot cursor. That's already a bit more readable. That's good.
Mm.
We can also then assert that these are equal a little bit more concisely. That we don't have to. We can just leave it like this. This is simpler than using metadata equal or something.
Yeah.
But then
Cool.
if we ever add another field, we won't get the assert there for free.
Yeah.
I don't
And
think we will ever.
and you can't just do a equal equal on the struct itself.
Yeah, you
That's a sub.
see the metadata equal. Um, I think that's actually the best way to do this. I think we
Yeah.
don't. That just takes any types, right? Yeah, cool.
Yeah. I thought we could do, instead of next adjusted, we could say adjusted underscore next to put the qualifier last as the suffix,
Okay, sure.
and it'll work nicely on those two lines there. And I don't know if we want to call it, instead of adjusted, we can just call it cursor, cursor and cursor next.
Um, hmm. Not sure if that. Yeah, Justin's not a great name. You're right. I think the cursor isn't really any better. Because cursor then like I feel like it kind of conflicts with the reverse dot cursor. Because we don't use it in the same way. We actually want it to be different from reverse dot cursor at any given point in time.
Okay.
Um,
Well, then adjusted is fine. Uh,
okay, cool.
Maybe start we could call cursor. Uh,
Reverse dot cursor.
yeah, start cursor. But then maybe that's too much. We're gonna when we
I think just start is good. And
yeah.
then adjusted. Or should we take a cursor that is the argument to absolute index? Do we use that anywhere else? Hmm. So we're shadowing this function with a variable with a parameter here currently. That's not going to compile.
Okay.
Um,
Yeah.
let's see what's the fix there. Um,
Maybe change the
We could call
parameter.
this like cursor to absolute index.
Yeah.
And this takes in a cursor perhaps instead of these things.
Yeah.
Um,
I would say maybe we can just say absolute index from cursor. Then,
that's even longer then.
yeah,
It doesn't really matter which way to me.
yeah. We
Um,
we we did it in
Still
that.
short enough.
Yeah, we did it in that order for the table table info for Keynote. Remember that because that way the thing that comes last, cursor, corresponds to the argument that's being passed in. So yes,
Yeah. Where is that now? I think we deleted that
okay.
at some point. You can
It's
do down from
something.
there now.
Yeah, it's something that uses root table nodes array.
Hmm.
It uses that internally. There we go.
Iterator start table for Keynote. This one.
Yeah.
Cool. Now,
So maybe
um,
then we want to
we,
call it, instead of saying from cursor, we can just say for cursor, absolute index for
yeah,
cursor.
that's cool with me. Okay, so level.keys to absolute index. Now we pass in just start instead of these two things.
Yeah.
Where else we use it? Here, again, we just pass in adjusted.
Yeah. And then I think the method name has changed now, absolute index for cursor.
Indeed. It's only these two calls too, so it's perfect to do
Yeah.
it like this. But
Yeah.
maybe we should just pass in a cursor instead of an absolute index. I think that's actually even better. Then we can just get rid of the function entirely
Yeah.
and just you start an iterator, you're passing a cursor.
Yeah.
Um,
Yeah.
so also hold up. Why are we passing also a keynote though? Is that right? Oh, well,
You see that I think that's a symptom of the problem where we decompose too soon into an absolute index,
yeah,
then we pass the
you're right.
keynote.
So yeah, we should just not. Yeah, so we should just pass in the cursor here
Yeah.
directly.
Yeah.
Um, and then this is the same start. We do the adjustment to find the actual start node inside here, I think, right?
Oh, wait,
Because we do the
Isaac.
first absolute index thing here. Yeah. Okay. Cool.
Yeah, there's actually a difference. There is a reason why we do it this way.
Yeah, because there's this thing, right? Isn't there? This we don't have this inside that other thing. We aren't using this right now. I think we might have gotten rid of this by accident.
I think
We need to fix this.
we're supposed to actually be using this one to. There's actually a
Or the second
discrete.
one.
Yeah, there is actually a good reason why we pass absolute index plus the key node, because the absolute
Yeah.
index is the actual correct index. The other key node is
Yeah.
not related to that cursor. It's another cursor that's just a hint. Uh,
Yeah. This is right now, I believe.
yeah, that's the thing.
This needs to be adjusted to Keynote. I think I never finished updating this. Is what happened.
Yeah,
So we used to have this. I'm pretty sure. But now we do again.
yeah, yeah. I think that's right.
That seems fine.
Okay. And do we want to pass in
Yep.
the?
Yeah.
Is it safer? It's safer to pass it in as an absolute index and still to have that option because that way you can go across different segmented arrays. The absolute index means the same thing.
Yep.
Yeah,
These calls are both right now. I'm pretty sure because this is in the
yeah,
same segmented array.
yeah,
It's also not called Keynote anymore though. It's called just Node. Um,
Okay.
And this is no longer needed. Here it's just node as well.
Yeah. It's actually better to call it node because that is then across different segmented arrays. Yeah.
Hmm? Yeah,
Um,
because it works for
yeah.
working for both segmented arrays.
Yeah.
I think in this case, I'm gonna leave this one called Keynote though, because it is a
Yeah.
keynote.
Yeah. That makes
Um,
sense.
but in the type, it should definitely be called node.
Yeah.
Yeah, cool.
It's interesting how like improving the names actually makes it safer. Like it just keeping the code
Yeah,
actually
indeed.
becomes better and stronger.
Cool. So this is looking pretty good now. We got a to do to add assertions. Are there any assertions you can think of here?
Um, in our actual segmented array iterator constructor, I'm not sure if we check start node, the hint that we provide against the absolute index and direction. If we cross check everything there well enough.
Okay, so what exactly do you want to check? We check that start node is a valid node,
Yeah,
and we check that the absolute index is a valid absolute index.
yeah.
Um,
So we could do one more check where, according to the direction, we you see at the moment start node and absolute index are orthogonal here.
right.
But the caller's intention is that start node is going to be before or equal to the start node for absolute index, according to direction.
Oh yeah, I see. Okay, so we can do assert um, array. There's yes, which direction? You're right.
Yeah,
Or just
put
add
it
this
in
thing.
there. Yeah.
Um, oh, we already do that here. Look,
Oh, okay, great. Array.
and same thing here. So we're good there.
Okay, and can we just check that that's correct? The first absolute index for that start node must be less than or equal to the absolute index. And
Yep,
descending,
that's good for ascending. And for
okay,
descending, it's the absolute index is less than the last absolute index of the start node.
okay, cool. That's great. Nice.
Yeah.
That's another thing that I learned, like just doing some cryptographic protocols. I don't do cryptocurrencies or anything like that. Just like cryptographic protocols. Like often what they do is what makes them, like what made TLS very unsafe, like SSL and stuff, was there was too much stuff that wasn't bound together cryptographically. Too much stuff that could be orthogonal or loose or and like
Yeah.
noise is much better because everything is bound like cryptographically. It, so it's like the single
Cool.
use principle and the binding principle where everything intention always needs to be bound.
Like, yeah, things like check that they're in sync, I guess. That's kind of
Like,
what it is.
exactly, yeah.
Yeah.
Yeah. So
All
that's
right.
also why we do that, where we jump from start to adjusted, and then we manipulate adjusted in terms of reverse. That's why we've got that step where we bind the two together to check that we're in
Yep.
sync.
We make sure we assert here. Yeah.
Yeah.
Makes sense.
Yeah.
So we could also just use reverse that cursor here. Like we don't need to use start.
Yeah.
So I think it's actually better to actually assign adjusted to a reverse that cursor and then assert is equal to start.
Exactly. Yeah.
What do you
Yeah.
think about that?
That's
So
also
we're always
fine.
doing the
Yeah.
same assignment.
Yeah.
Um,
That's better because now
or we can like here assert that reverse that cursor equals start.
yeah. That's actually a better way of showing it. Okay.
Yeah.
Cool.
Yeah.
Much better.
Cool.
It's always like some of the security stuff I did. I also found it's the same idea. Like it's always where there's ambiguity, where two things are not quite in sync, where there's a gap. So this way
Yeah.
you're closing the gaps by binding stuff. Yeah.
Cool. I can't think of any more assertions we can add here, to be honest. I think we've got
Yeah.
The iterator asserts everything I want to assert, or everything I've thought to assert already.
Yeah.
Um,
Cool. We could do one more where we take the start key out of the reverse iterator, but actually it's pretty difficult to do. We could if we had a normal level keys forward iterator, we could compare that, but that's overkill. So remember what?
yeah,
Uh,
yeah, I think that's not really worth it.
no.
Because if that's wrong, or if the iterator thing is wrong, I don't know. I
Yeah.
think we just have
No.
to test the iterator is what we really need to do.
Yeah.
We want test for the segmented array, and then that will cover that
Yeah.
failure mode.
Cool. Adjusted next.
Yep, this all seems good to me.
Yeah. So on line 8, we capture the current cursor, which is the start cursor. Then we get the start key there at that position. Then
Yeah,
we capture the cursor again because we're about to change it when we call reverse next in a while loop. If the keys are then different, then we're going to um, break, and then our cursor will remain adjusted. We'll discard adjusted next. But if they're equal,
yep,
then we're going to update our cursor again. We're going to swap it out. Uh,
yep. And if they're equal, we'll update the cursor adjusted to the key that we're equal with. And
yeah,
so adjusted, the cursor adjusted will always correspond to a key that's equal to our start key.
yeah,
I should put that in a comment just to make
yeah,
sure. This cursor will always point to a key equal
to our start key.
to start key.
Yeah,
I think I also want to do it like this. So
yeah,
then it like matches this with the start key.
yeah.
Um,
That's nice.
and then you also have this one's like always match with the next thing. So that's actually what it is. Adjusted next points to the thing returned by this.
Yeah, that's
Um,
perfect. That's really, really nice, like that grouping. Shall we, on that comment, Isaac, this cursor will always, should we just add a full stop or a colon?
oh yeah.
And then uh, there is one more assertion, although we can't act, no, we can't do it. Like we could we could go into level keys for the cursor and get the key that's there and then assert that it's equal to
Yeah, we could,
start key.
but we don't. Yeah, we don't really need to. I feel like we could. Yeah, it'd be like it would look like this. Assert or compare keys, start key. Then here we need to do like level dot keys dot node elements. Um, adjusted dot node, and then adjusted dot relative index. That'll give us then the key, and
Yeah.
then you can check that they're equal.
We maybe
That's
want to
pretty.
on a segmented array just have a get method that takes a cursor and returns the element, or just an element method, level keys element, and it takes a cursor,
Sure.
uh, element for cursor. Or we could even just
Node
say
element. Element.
it could even just take a cursor here.
Hmm?
No, no, perfect as you got it.
Returns T. And okay. And then we
Nice.
just call element here. And
Yeah,
then this is a fine assert to do.
yeah.
Um, yeah, just adjusted.
And
That's not
then
too bad now.
Yeah, and we can do that again after our adjustment loop because that should still hold.
We can actually do like a little bit better. ASSERT.
Yeah,
I think I can get rid of this now. We can assert start key is equal to, yeah, we can do the same thing. Cool.
yeah, nice.
Yeah, I think we've made this pretty safe now.
Yeah,
Cool. So we started to a new function.
yeah, and then embed it within iterator start so that iterator
Iterator.
start
Yep.
returns the correct start to begin with.
And so we want to leave, we actually want to leave this iterator creation here, I think.
Yeah,
That's what should happen in this function. We want to like return adjusted essentially from iterator start.
yeah, exactly.
So let's just put this in a helper function because there's two places we need to call it here. We need to call it in this case and in this case, but we don't need to call it in this case because we're already, yeah. Maybe we do.
We do.
Um,
If we, depending on the direction, if we're descending,
yeah.
then we need to go,
No? Are you sure?
then we need to go right.
I feel like I figured this out last time that we don't need to call it, but I'm not remembering why.
Yeah.
I think we're not actually gonna. I don't think we ever hit this in a descending search. That's what the comment says at least. It's
Hmm.
not in a descending search.
Of course. Oh, it could be because you see the descending search is searching on key min, but so, oh no. Shall we do the helper and then come and work out how we plug it in?
Sure, yeah. Let's do that. Well, I got this in my like paste
Yeah.
register.
Yeah.
What do we want to call the helper? Iterator
Start
start
correction.
um,
Correction?
um, correction or adjustment. I want to call it.
Yeah, or fixer upper.
Let's call it adjustment for now.
Adjustment's better.
This returns a cursor. Uh,
Segmented array cursor.
I'll also take a cursor, I believe. Maybe we just make it take a keynode and a relative index as two arguments. We really need to pass them. I don't think we really need to pass a struct here.
Yeah.
This can just take a keynode, or maybe it's nicer if we do. So we need to take here level and a cursor. Self or start. No, this type name is really long.
Uh,
I kind of want to just call it cursor, but that's also then would be not
I,
here.
th
It's from the
I,
segmented array.
I think within segmented array, it makes sense to just call it cursor, but outside, then it's nice to call it segmented array and segmented array cursor.
Yeah, we're outside here, so that wouldn't help us in
Yeah,
this case.
exactly. Yeah, yeah,
Iterator start fix.
yeah. We're kind of like the goal here is to get outside of the cluster. So we're trying to get to the extreme or to get to
Iterator.
the boundary or the edge, because the start is somewhere in the middle. So these are just ideas for names.
We call it just like scan to start.
It's more, maybe we could call it just even start boundary, because the start itself is somewhere in the middle.
Sure.
And we
That
just
works. That's
need,
98
yeah,
columns.
Boundary should just have an A, I think, unless my American spelling is off.
No, I think you're right.
Boundary.
Keyword. No, D.
That's it. Yeah.
There we go.
Cool. Is that the correct US spelling?
Yeah, I'm pretty sure.
Okay.
That looks right.
Cool.
I'm not happy with this variable, with this argument name now, because it's not actually the start we return. I think we should return start and like
Yeah.
flip our names around here. So then we
Yeah.
have
Cool.
what do we call this? Just cursor, perhaps.
Yeah. Or just call it somewhere.
And then we got that 2D done. Cursor.node. It's actually like a key cursor. We could also just call it like, I don't know. Keys isn't the right thing to call it, but
Yeah.
it is a key cursor.
What this function does is it takes a cursor to a key and it returns the boundary cursor for that same key.
Yeah. Where's that cursor?
But I actually like how you're calling it cursor as the argument, you know?
That's what I want to call reverse, just iterator, I think. Or it. Because it's clear that we're going in the reverse direction. Oh, we need the direction in here now, don't we?
Yeah.
Guess we need to pass it down after all.
Yeah.
I'll
Yep.
wrap this then.
Cool.
I think it should be called key cursor then, to be honest. I was just making it shorter to be.
Yeah. Nice.
Here we also need direction. And then you can come back here and actually maybe do an assert if we're ascending, if we think we can.
Yeah.
So iterator start takes a direction now. And it will just return a start, and then we'll just use start here.
Yeah.
Cool.
The only thing I'm not sure now is this iterator is returning, we're actually iterating within our key nodes. Not, you see, so the
Yeah,
start,
this is the wrong thing.
yeah.
Sorry, what you were saying though?
Yeah, on line 2, iterator start table node for Keynote. That can only be called that can only be called for the min key of a key node. But our start cursor is adjusted.
Oh, is that right? No, that's not true. It's it just gives you a key node.
Yeah.
Doesn't know anything about keys. This will just give you the key node corresponding to where this thing starts, I think.
Yeah. Yeah. You see, at the moment we've got a bug where if say we're descending,
Yeah.
and we're gonna iterate through our keys segmented array, because we're gonna reverse through there. So we're descending. I don't know, from your perspective, let me just get it right. Is this descending if I go that way, or is it that's descending? Yeah.
I think it's the other way, that way. Yeah.
Okay, so that looks like descending to you. Okay, cool. So if we're descending this way, we're first going to fix up by going this way.
Yep.
And when we go this way, as we iterate through keys, we are then going to stop at a relative index somewhere in the key node.
Yep.
Then we're going to accelerate our iterator, we're going to return the table node that corresponds to the min key of that key node, which is over there somewhere. So that's correct. Then we start our iterator even further back, and then we go that way.
Yep.
Then if we're ascending, this is ascending, and we're going to start our iterator before the fixer-upper somewhere over here at a keynode. But now when we do the fix, we're actually going to go this way and then past the keynode, and that's where we're going to start our iterator. So I think we're going to hit an assertion failure where in ascending where we check the key. Our keynode hint, I don't think is correct.
What assertion do you think is going to fail?
That assertion,
I'm not seeing a bug still.
yeah, where if we go into the, I think it's within manifest, our iterator, uh, where we
You mean
speed,
segmented array or this iterator?
maybe it's in segmented array, our constructor where according to the direction we assert, yeah, it's in segmented array. Yeah, it's those, that one is going to fail, I think, because our start node, we're
Which
passing
one?
uh, on line
That's
four,
fine.
line four.
This one?
It's because we're
That's
just
actually
passing,
that's still fine.
we're passing the same start node as our absolute index, which is not correct. So when we do the fixing up of the,
That is correct. We haven't changed anything about how what we do here. We still
okay,
pass.
okay,
This is the absolute index and the keynode. Um, well, here start contains a relative index and a keynode, and
yeah,
then we go here keys absolute index for cursor. We get the absolute index of the table info, and the keynode we convert into the corresponding table start node,
yeah.
and then we always iterate. Yeah, there's no we haven't changed anything about this, what we
Yeah,
just did.
I was just
Um,
wondering if we can do that because the, yeah, okay, okay. Are you sure you can't find a bug in there?
yeah, um, is table node for keynode, and we always iterate up here, right? Well, I'm in the wrong thing now. I want to get to go to yeah here. I think there might be a bug. You're right, because I think we can't iterate down here. I think we have to iterate up, and we're doing that wrong right now. Um,
We also have to think it through in terms of the direction we think of key max or key min, but our start node is only in terms of key min.
yes, that's why I think we need to iterate the other direction here potentially. I'm not totally sure yet. Um, yeah, I think this is wrong currently for descending only. I think for ascending, it's there's no bug at all.
Yeah,
Um, yes, let's like maybe draw this out a bit.
yeah.
Um, that could help. Okay. Draw it just like black.
I just
So
I just had
let's
like
draw both.
a hunch that it was maybe we had got out of sync. So
Yeah,
because of doing the correction, versus our start node that we get from table node for
so
keynote.
I'm gonna make like pretty big keynodes. These are the keynodes.
Yeah,
We'll have table nodes as well.
yeah,
Say we
nice.
have like several table nodes per key node.
Yeah, that's great.
This is not gonna be super pretty. It also maybe better if they don't line up perfectly, because they're gonna be like all different sizes actually in practice potentially.
Yeah,
Anyhow, cool. That'll give us the base diagram. Now, um, Yeah, so let's think about what we're searching for now. Um, so they were doing like an ascending search, um, starting at like a key somewhere here, ending at a key somewhere. Well, we can just look at the start for now. Saying we're doing ascending first though,
Cool.
to make sure that case works properly the way we think we do.
Yeah.
So we'll end up. We're not gonna look at the adjustment yet. We'll say this is after adjustment. This is our start key. Um, inside this key node.
Yeah.
And then we'll go Keynote to table node will get us then to this table node
Yeah.
right here. You
Cool.
agree with that so far? And then we'll iterate up until we hit this table node.
Yeah.
So that's good for ascending.
Yeah. That's cool.
Now, for descending, um, we're gonna have the same thing here. The problem is that it's gonna give us this node. We're gonna start here. Then we're gonna iterate down, and we're not gonna
Yeah.
find anything.
Yeah.
Um, Actually, I think we're going to stop right away, actually. But
Yeah.
then we'll skip data.
Yeah.
I think our iterator will actually terminate immediately, but we'll skip data. So what we
Yeah.
need to do for descending is like to actually um, just add one here. Do we always just add one? Is that the solution? Um,
Yeah. So we need to see that start node as a hint. And if we do add one, if we're in the last node, we're still going to start at a table info that's before the absolute index. So we just need to check there that we actually get that right.
um, I didn't really follow what you said. Are we ascending or descending in this example?
Okay, so we're descending. The start node table info is going to be a little bit left, more left, or it's going to be that one if we drop down now into table nodes, a bit
Yeah, to
left.
me this.
It'll actually be left still. It's going to be corresponding to the key min of that key node. So it's going to be the fourth one from the right. Um,
You're saying it's this one.
yeah, because we're going to pass that key node as the
That's
start
what
node.
currently happens. Yeah. But I'm
Yeah,
saying we shouldn't do that. We should use this plus one. Get the one past the out of bounds and then start iterating from there.
yeah, that's fine. But yeah, then we go from there. Or we need to use the very last table info in a key node if we are descending. So if we're ascending, we use the first. But yeah, we can't get to the last. Yeah, no, just the plus one is fine, and we just need to handle the out of
Yeah,
bounds. So,
exactly. We just need to handle the out of bounds at the end and iterate from the last. Yeah.
but do you see what I mean? Is if we do have the out of bounds, we'll get the only table info we can get is the fourth from the right.
What do you
That's
mean?
our our um, that one
You
there.
mean
Yeah,
this one?
yeah, that's the only one in our we've got our in our root node, the root has got key mins and then it's got the corresponding table infos for those key mins. That's the only mapping we've
Right.
got there. So if we are out of bounds on the right,
I'm
we just
saying
have
we need to add like one thing to that mapping. Um,
okay. Yeah.
I guess, or I'm not sure what I'm saying yet. I'm saying we need like some sentinel that says, okay, you're outside that mapping. Do something else and just give us the last table
Exactly, yeah.
or
I'm
like
with
the one past the end table here. Um,
yeah. We can also
I
see
think I can fix this. I see a couple ways to fix this in code.
Yeah.
Are you happy with like how we should fix this now, or?
Yeah, we've got it. So let's go for it. This is
Okay.
a nice
And let's check
diagram.
the other end just to make sure there's nothing weird here.
Yeah.
Like if you land exactly here, then it'll still be the same keynote, so you'll get to exactly here.
Yeah.
Um, and that's for fine for descending too. You'll get this one if you're descending,
Yeah.
then go down. Yeah, the other end seems fine. There's no out of bounds on the lower end, I don't think.
Yeah.
Yeah, because really what we want, the thing we're missing is this one here, because this is not actually stored in our array where we convert. Like
Yeah.
this boundary. This boundary is stored in the array where we convert stuff.
Yeah.
Yeah.
For
I
ascending,
think we
it's
just need like
safe because we always go earlier to the left. But for descending, it
yeah
isn't safe because going earlier to the left cuts the iteration short.
yeah. So back to manifest level then, and
Cool.
here we've got this iterator start table node for Keynote. Okay, and so here I think we should just take a direction is what we should do.
Yeah, and I think the problem with it's the interface that led us astray. We need a better interface it's too simple. Um, it needs to be smarter according to the direction. So we actually want to pass in an
Yeah.
absolute index here, or a cursor.
Why?
Um,
Why not just pass a direction in the Keynote?
yeah, no, but what I mean is if we had passed in like a cursor to begin with, plus the direction, then it would be. I mean, I'm just saying we can handle it just with the direction, but I think if we had made it a more powerful method, then it would have we wouldn't have had this
Yeah,
bug.
probably.
Yeah, cool. But I'm not blaming or anything. I'm just trying to I'm learning, you know.
Cool.
I was thinking of this just as a simple mapper, you know, and it needed to be more of a
Okay.
helper.
And so now I think we want to have another case where we say like direction. Well, first we can assert the keynote's inbounds. That's still fine. We say if direction equals dot descending keynote plus equals 1, and then if if key node equals level dot keys that node count, return. I'm just kind of sketching this out.
Cool.
What do we want to return? We want to return.
We want to get the elements for the last
We actually want to return the last valid table. So
in
level dot
tables.
table
Yeah.
dot node count -1.
It isn't correct still.
Are you sure?
Yeah. Uh, because we're still gonna, well, I mean, it is correct. We're gonna get the last node, but then we need to still check we need to still check in our iterator that we then do the same edge case there as well to jump. So I
I
think,
think we do
we,
this correctly in the iterator. I'm not sure, but let's look at this.
yeah,
So
what we really want to
so
do
after
is
no,
have that
yep,
helper.
this is all correct actually. This is fine.
Okay,
Because here we look at the last absolute index in the table. So now, we don't actually need to go out of bounds. I was wrong about that. What we need
yeah,
to do is here. Um,
get the
actually,
last.
we can make this. We can make this. Yeah. We want to return like the first. We either want to map. So for descending, if we look at this, we actually want to map to this. This would be the ideal table to map to.
That's what I'm thinking
Um,
too. Yeah,
yeah. And so for this one, this is the ideal table to map to.
yeah,
Even if you have your key here,
yeah,
you still want to go to this
the
one because
last.
then we look actually at the last thing entering the table. We would start here for our iterator loop, which we do
Ex
correctly already.
exactly. Yeah. But I think
Cool.
what will make that routine safer for this is if it actually returns a cursor, not just a key node. because then when it returns a cursor, it can return either the first table info in the node if we're ascending, or it can return the last table info if we're descending. And then wherever we use this, it's just safe.
Okay, and so you're saying we should just kind of change the API of the iterator to take a cursor here instead of a
E-
start node.
Exactly, yeah. Yeah.
Absolute index and then start cursor instead of start node.
Yeah. I don't know if you think, I mean, maybe we don't, it just, what are your thoughts, Isaac?
I'm not really convinced yet. Um, I feel like that's like we need to then expose these helpers outside of as hub functions, which they aren't right now. Right now, these are just internal helper functions for us here. And
Yeah,
so to make this take a cursor, we don't have to like call these from the calling function to make the cursor right. I
yeah.
think just taking a node here is better. Um,
Okay, and then taking start node, if direction is ascending, it'll start from the first element of the node. If the direction is descending, it'll start from the last element of the node. Then we just
yep.
must make that clear, like document the start node argument and say that that's
Yeah,
how
that
it
makes sense.
works. Uh, cool.
Um, um,
I think it's a good call also, like that we don't pass the cursor because then we going back and forth across the two namespaces. Cool. Maybe we can drop the direction and just say, if we are
if
ascending, we
it's
start from the first element of the node and ascend.
or just if ascending.
Yeah, yeah, if ascending. Cool.
That seems good. They actually
Yeah,
get the line. It lines up again.
yeah,
All off by one character. It's like kind of weird. These parts line up.
yeah, yeah, that's weird. And
Monospace
then,
fonts are funky.
yeah, yeah. Maybe we can say where we say this just, we can say the start node allows us to skip over nodes and as an optimization and then colon because we're then gonna fill it out a bit more. Okay, cool.
Did I get that right?
Yeah, yeah, perfect.
Cool.
Maybe
All
we
right.
can, just to make it a bit clear, we can say the first element of the start node and ascend, or last element of the start
Of
node.
the yep.
Yeah, cool. Yeah, perfect, Marcus.
Cool.
Nice.
And now this is all good too, I think, right? Yeah. This is good style. Are you happy with this stuff all in one line?
Yeah,
Um,
we can avoid the branch if we only check if Keynote is out of bounds with for descending direction, because we don't need to check it
do it
for,
like this.
yeah.
Yep. Cool.
Shall we?
That's still like, short enough. I kind of want to like wrap this though because it's kind of long.
Yeah, I think so.
Um,
I think so too.
like
I'm still getting my head around it. I'm a bit slow this morning. Uh, if it's descending, bump the keynote. If the keynote is at the end for keys, then go to
you want to
go
go through a
to
few more examples?
yeah. Or then we're going to return
Yeah.
the last
It's
node
only the
of
case if it's
tables.
yeah at the very end. So another example could be just like here if we're descending, or yeah. Then we're gonna get this key node out. We're gonna add +1 to get to this key node
Yeah.
boundary. Then we're gonna that ends up that has this as the start node, and
Yeah.
so we're good for anything we had for any point inside this key node. That's the one we want to use, even
Yeah.
here.
Yeah.
Well, here actually it would be better to use this one, but we can't know that in advance, and
Yeah.
so without storing more data.
Cool.
But yeah,
Okay.
that works. And then yeah, also for this one, it's the same thing. No matter where you are here, you want to use this one if you're descending. And
Yeah.
here, that's the only edge case where you always want to use the last one in that node.
Yeah. And that's because the table info for the key min of the last key node.
The
Um,
table info for the key min last key node is right here, I
yeah.
think, roughly.
And then there could still be more table nodes after that. That's the problem.
Indeed.
Other,
Right, because there's more table
otherwise,
nodes.
otherwise it would be okay just to return the table
Yeah,
node for
you're right.
that.
If we had the same number of key nodes as table nodes, there'd be no issue here at all. Um, or if there happened to be only one table node for the last key node,
Yeah.
we um, oops. Oh man, can you not like redo stuff? Why? Yep, I don't know how to redo.
Oh,
Anyhow.
okay. I wonder if we've actually got still a little bug like that, where
Where do you think?
if we go back to our code, we if we're descending, we increment the key node. But I
Yep.
think we actually want to be getting what we actually want to do here is before we check direction, we want to get our return, our result, so root table nodes for the key node. We want to actually get to the table. We want to do this all in terms of table nodes, not in terms of key nodes where we do the increment. Because say here we are, key nodes, we're in the middle, we're not at the end. So you see here we do key node +1, then we check if we're at the end. So say we're
Yep.
in the middle, right? Um, then we get to the corresponding table node and we return. Or we're going to get to the, we're going to do key +1 if we're descending. We're not going to be at the end. So we go straight and return the table node corresponding for the next key node. But it's actually possible for 3 table nodes to correspond to like 2 keynotes. So actually we want to be doing the +1 in terms of the table node. I think we might need to draw it, but
Yeah.
it's,
I don't think we do. I'll draw it though. So you said
yeah,
3 table nodes and corresponding for 2 key nodes. So say we've got only 2 key nodes.
yeah,
Or let's make it a little bit bigger. I'll do
yeah,
like 3 4 key nodes or something like that. And then for
yeah.
table nodes, how many do you want like corresponding? You want like table key nodes like split across the boundaries, I think? Like something like this.
We we want to do more than 2 table nodes per keynode.
More than 2. Okay.
Yeah,
So like 3 table nodes or 3.5 per key node, something like that.
yeah, yeah.
Oops, that one's a little bit funky. Okay,
So
and then we go
let's
back to
maybe,
red now.
shall we go back to, okay, let's start on the right keynode if we're descending.
Ooh,
That kind
okay,
of, because this was how I thought of it.
this is a
Uh,
cool, okay place to put the key we're looking for. Like
yeah,
just put
yeah,
it here.
yeah, thanks. That's awesome.
Okay,
And then we're going to get to the table node for that key node, which will be the one that's fourth from the right.
this
That's a,
one.
yeah, but this is now a table node, not a table info.
Yep.
Then we're going to go to the last element of that table node.
So right here.
Yeah. And you can see that we're actually still cutting our iteration
That's not
short.
what we're doing though. We're going. We're This code doesn't do that though. The code says we're here. Okay, we're gonna look at the last table node in the whole array. This is table nodes, tables.node count. This is then like 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the node count minus 1 to get to the last node that's valid in the table nodes array.
Okay.
You see how that works?
Yeah, that's okay. Thanks that we can run through this. It helps to
No problem.
just be sure. I'm still not convinced. What bugs me is that we do the increment in terms of key node, but table nodes and key nodes are.
That's correct though.
Hmm,
Because if we did it in terms of table node, check this example for example.
okay.
Say we're looking for this.
Yeah.
Um, and then so we'd use our array to translate to key node or to translate the key node to a table node. Then we get to this table node.
Yeah.
If we get an increment by 1, we're here. But that's
Which is
not
wrong.
enough.
Yeah.
We need to increment by key nodes that we get to here.
Yeah.
We want this one.
Yeah. Okay, cool. Now I'm convinced. Okay, cool. Can we thanks that we could work this out.
No problem.
Shall we jump back at the code then and just take another look?
Yep. We could add some comments here too. It'd probably be worth it.
Yeah, yeah.
Um, since the corresponding table node in the is a lower bound.
That's it.
Lower bound to add 1 to make it an upper bound if or when descending.
Yeah.
Nice.
Nice.
If we were already at the last keynote, can I put this in here? I think it's nicer. Yeah. And maybe like add a space there. If we're already at the last keynote, then we should instead return the very last table node.
Yeah, that's awesome, Isaac.
There we go.
Nice.
Happy with this now? I think I'm happy with this.
Yeah. It's really tricky,
Good catch.
Yeah, thanks.
Oh yeah, definitely is. It helps so much to draw it out too, I think.
Yeah.
At least for me.
Yeah. Yeah, definitely. I don't know. I think we should try and draw it out in the comments here as well so that we document it like other people can
Drawing
actually
out in
see
the
it.
comments is hard.
Yeah.
Nifty says for me too.
Hey,
Yeah,
nice.
it's crazy how visual this stuff is, even though it's just like bits inside a computer.
Yeah. Yeah. I read, like, I've been following, because like Mitchell Hashimoto, like you say, he's been in the Zig Discord, and then on Twitter also, he's been posting a lot of Zig stuff, which is cool. But
Yeah.
something he said, otherwise, he said, like, the hard, it's not like communicating with the computer that's tough, but with other programmers, like conveying the ideas.
Yeah. The computer always does exactly what you tell it to. Other programmers don't.
Yeah, yeah.
All right, cool. Um, are we happy with this? Should we like add some more spacing in here, just like for
Yeah,
beautification purposes?
yeah. I
Um,
was I was just going to suggest that it was bugging me that that precondition we didn't have a space new line.
all right, I think
Yeah,
we're not using this in the right way now. We need to like pass a direction, I think.
yeah,
Um, iterator start. Yeah, here we need to pass the direction. Cool. Now we've got, yeah, I think we actually have this correct now.
mm,
So we'll get the right start thing here. Um, iterator start. Oh, we don't use this function. We need to use this function. That's the missing piece here.
mm,
And I think we should just use it everywhere. I think we shouldn't try and do fancy things.
yeah,
Um,
yeah,
whereas this will take a cursor right now. Should we just take separate? No, taking cursor is fine. Let me
yeah.
just like wrap this thing. Dot iterator start boundary
Are our cursor
and just
types,
do.
are they both 32-bit, those two fields?
Yeah, they should be.
Because then it
Um,
is nice where we make it a bit more descriptive so that people can't ever flip it around and swap the order
yeah,
accidentally. Yeah.
yeah, that's a good point. It makes it more safe for sure. Yeah, you know, some ways I kind of wish like function arguments could just be a struct always, you know? Like there's no reason to have I kind of want to try a language where function arguments the only way to pass arguments to a function is like you give a struct, which is the argument type or
Yeah.
arguments type,
Yeah.
and then you just like set the struct fields and they're always named by default then.
Yeah.
Um, maybe unnamed function arguments are a foot gun, but
Yeah. It's okay so long as you always mix up your types. If the types are
yeah, that's true.
mixed, then it's fine.
I mean, it does make things a lot more readable.
Yeah.
Um, so let's copy this though. Do we really? We don't really know if we need to do it there yet. We can look at that right now though. Let's do
Yeah.
it everywhere first. Okay, so out of bounds to the left. So start the search in the first table in the level in that case of an ascending search. Does this all? Yeah, this always means out of bounds though. It doesn't mean an
Mm.
exact match. And so, um, yeah. So for a descending search, we could then return null.
Yeah.
And for an ascending search, we always want to start at the same thing. So we don't. This is not necessary here. I'm confident in that.
Yeah.
Because here we know that's not an exact match because this was false. Um, but the root.result.index was 0. That means that we didn't match, or the key we're searching for is less than all keys stored in our
Yeah.
manifest level.
Yeah.
And so for an ascending search, that means we want to start at the first key that's actually in our level and ascend from there.
Yeah.
And there's no earlier key you could start at. You're already seeing the full range, so you don't need to adjust
Yeah.
anything.
Yeah.
For descending, that means that you're done right away. There's nothing else to look at.
Yeah.
Um,
I think we should actually, if descending here, we should return null.
I think you're right. Yeah.
Yeah.
Um, switch, because we have the direction here already, so we might as well, you know?
Yeah.
It makes it more obvious then.
Yeah.
Switch direction. Turn that. Descending.
Because
Turn null.
I've been thinking like there's two ways to think of the safety here. The one is if the iterator cuts short, we like obviously losing data, it's terrible. But if it also goes too long, it's also another form of data loss because now stuff is getting into the wrong place or we're getting the wrong result.
Yeah.
Um,
Um, outbound to the left. Um, oh, I need to fix that comment. In the case of a descending search, where or we just say I think we just say we are already done.
yeah.
Um,
Or
all right.
we could describe it. because kind of returning nulls also shows we finished, but we could say, or we could say both, like we are already finished because the earliest key min is greater than the key max.
Here, the first
Key min is greater than the key max.
entire level
Yeah.
is greater than the target key max.
Yeah.
Oh, actually, I wrapped that too much.
Yeah.
Should probably maybe set this to 100 by default, but 80
Cool.
default is nice.
And there's just, sorry, Isaac, in that comment where we say we are already finished, we should actually just say we are already finished.
Oh yeah.
Sorry about that. You've wrapped it already.
Cool.
Yeah.
Out of bounds to the left, so start the search of the first table on the level in the case of an ascending search.
Yeah.
Out of bounds to the left. But that
What we,
said already works. Yeah.
yeah. Cool. But if I
Maybe
don't
we
know
should
what
be
you,
a little bit more explicit and talk about the key mins.
yes. Yeah.
So let's try this again. In the case of an ascending search, we start at the first element, or the first table level, since the target key min is less than the table. How's that?
Yeah, that's cool. And then maybe above the switch direction, we can add a comment saying out of bounds to the left, colon.
Left. Cool.
Okay, cool. And then in the case of a descending search, we could add a comma like we've got
Sorry?
Our second comment on line 8. In the case of a descending search, and then after search, we could just put a comma like we've got above.
Oh yeah.
Yeah. Yeah, these are nice.
These are both exactly 100 columns. That one's 99. Okay. I'm happy though. This looks
Yeah.
good.
Yeah. Awesome. So if it's an exact match, we do need to still fix up the boundary because we just,
Yeah, we do, because that could
they,
be an exact match in the middle of the array somewhere.
yeah,
This could be the exact match of this key here.
yeah,
And then there's actually there's actually another key with the same key min, or
yeah,
there's another table with the same keys min
yeah,
that are there and there with different time snaps.
yeah,
Um,
yeah.
yeah,
Just on a meter note, Isaac, have you got your IRC open as well on Twitch?
I do, yes, on my
Oh,
other
okay.
monitor.
Okay, cool, cool. Yeah.
Yeah.
Then, yeah, cool. So we need to do it there, and we're handling it right for out of bounds to the left. Oh, out of bounds to the left. Okay, I guess returning 0, 0, like we couldn't possibly fix that up more because we're at the very first.
Yeah.
Yeah. Okay,
This is good, I think.
cool. And then further down, we're not exact. We're not out of bounds to the left. So then we go to the previous keynote. Is that correct, like for different directions?
Here?
Mm,
Yes. We've walked through this stuff already very carefully.
yeah.
We can do it again if you like, but I'm pretty confident in this stuff.
Yeah, I'm happy to go again.
All
Yeah.
right, cool. Let's do it. So, for ascending, now, so this is in the case of an inexact match.
Mm,
So that means we didn't find the exact key min. we didn't find a key min matching the key we're searching for. So in ascending, there's no key min matching our key min exactly. And
So
that means that our binary search will return us the index of the next greatest key
key.
min.
Yeah.
And so we actually then want to go back one to then find a key node that is corresponding to a key min. Okay, so here's an interesting case. I don't think this can happen, but this -1 might be bad because we need to scan potentially if it's like the same key min.
Mm.
We might need to scan backwards to the next key min instead of doing that. But this, since this operates on the root, I think it's not actually possible because we would have to have, so this is the case where that could happen. This is where when every single key inside a key node, including the key min here and the key min here, have this, or every single table is the same. And they all have different snapshot timestamps, I guess.
Yeah.
You think that can ever happen?
It could theoretically, like,
Yeah.
so in other words,
Yeah.
we've done a -1.
This will take us from here to here directly. But if these keys happen to still be the same, then yeah. We really should subtract until we find a key that's not the same. To be super to handle this case of where there could be like tons of snapshots that have the same key min.
Yeah. Yeah, they were like in the consensus in replicate.sig, there was 1 or 2 functions there and in journal. And I literally sat for days on them going over and over. And each time I thought it was correct. And then a month later, I'd go through it again and I'd find it was wrong. A month later, I'd go through it, I'd find
Yeah.
it was wrong. And I literally did
Well, this
that
is
like N times,
yeah.
So
See, I'm not convinced that this will ever happen in practice. I think that we might be. I think the code might just never. I don't think we'd ever hit this bug in any real world use case.
yeah, but we
But
shouldn't
we
have
should.
a bug, you know.
Yeah, we should fix it. Okay, yeah, this is not too bad though. What we want to do is we want to subtract 1 until we find a key that doesn't that is not equal to this key. So we have also the keys in the root slice, so it's pretty cheap. So we should probably say that this is possible in the rather unlikely event that there are enough that a key node is entirely filled by tables with the same key or min key or key min. Wrap this rather a simple root results index -1 isn't sufficient to give us to get us there, or that, and this is not entirely correct what I wrote here. It's that there actually has to be more than a key node, that over key node element count, is that what we call it? In segmented array, I think. Elements per node. Yeah.
Also, because here we're in the root node, so it's the key mins of key nodes.
Node capacity is what it is.
Yeah.
Yeah. But the root node corresponds to the key mins of the key min of the first key of every key node.
Yeah.
And so the thing that would cause this is if we have more, like over a key node worth of contiguous tables with the same min key.
Yeah.
That's a good way to put it.
Yeah.
Over a key node worth of basically
Eh,
it's implied that they're contiguous because we sort them of
yeah. And
tables with the
another way
same.
to say it is also just to say it's in an unlikely event that more than two keynodes share the same key min.
Yeah, that's good. Or that two keynodes, that two or more
Yeah.
nodes share the same key min. Um, to to the next key min.
Yeah.
Get to the next lowest key min. All right.
Yeah.
So now we need to.
It's just while we're doing the comments, our previous branch where we switched direction uh, on line 11, where we say since the target key min, that line, I think we say, I don't know if it's just the graphics buffer, but is key min there? We need to probably put an underscore. And
Yeah, we don't here currently.
okay, okay, cool.
Um,
Can put two there.
Oops.
The next one is fine. Okay.
Yep, and the other ones are good. The key
Yeah.
mins. Yep. Cool. So how we do this loop now? I guess I think we just do like const key node. Actually, we can just do it as a loop perhaps. Equals or well, that's just, I think it's a while loop really. While
While there
we
isn't
always want to subtract one, I think, but then we
at
we can always subtract one here, at least.
only the
But then we need to
first
check.
only the first time.
Yeah.
Yeah.
Then we can say like while. Then we need to check if they're equal. Compare keys while they're equal.
Yeah.
Well, especially we kind of want to like save the initial. But if we still use root result to index, well, compare keys. How do we get to the root key? I think we just index into root keys array. Or do
Yeah.
we have like a root keys? Yeah, we do. Cool.
Yeah.
Compare keys, level root keys, key node, level root keys, root result index. We could probably like have we already have root. Yeah, we
do.
do.
Yeah.
Awesome.
And that way we don't have
So now we
to unwrap it.
yeah, duplicate the bounds checks and make the code super verbose.
Yeah.
Root result index. So while these are equal to while this is equal, we're going to do what? We're going to subtract until we go out of bounds. If we go out of bounds, we just break.
Yeah.
Then we're stopped. We can also
So
put that in a loop condition then.
exactly, yeah.
So while we want to put that first perhaps, root or key node
Is greater than 0.
is greater than 0. If it's 0, we just want to stop, and that's the case as well. If it gets to be 0, then we just scan the whole array anyways.
Yeah. And root
Cool,
key
that's a little
node.
bit too long, sadly. So I guess we can do like that. And then what we're going to do here is we're just going to subtract 1. Okay. Here's a bug fixed.
Nice. That's a crazy bug. Like
That is a really crazy bug. That edge case is so we never caught that through testing, I don't think.
Yeah.
And I think it's
This,
possible because we only allow 64 snapshots,
yeah,
um, and if we have more than 64 keys per keynote,
yeah.
so we could also just add an assert about that instead of this loop.
No, I
I don't
think we
know. What do you
need
think?
the loop is better. How would we assert it?
We would assert that the number of elements in a key node is greater than the number of snapshots. They're greater
Yeah,
than the maximum number of snapshots.
yeah. I like this loop because it's a lower hurdle.
Yeah,
Um,
that's true. Yeah, you're right.
it
It makes it easier. It makes the code more correct, I guess.
yeah.
Like
This is a
there's
good
no configuration where this would be invalid.
yeah. I'm thinking like for our bug bounty, this will come into it when we're ready. Like once it's finished, it'll
Yeah,
come because it's part of the consensus. Because our consensus and our storage are integrated, so they're one.
yeah,
Uh, so this would have been either like a $8,192 correctness bug, or it would have
yeah,
been a $2,048 liveness bug. If um,
indeed.
But now it's a known issue and we fixed it, so it's pretty cool.
Yeah. All right. Cool.
Shall we do a 5 minute break and then maybe we can end when we come back, we can just take a look at this last branch
Sure.
for descending direction and like just put it all
Sounds
together.
good to me.
Yeah.
Um, yeah.
Okay.
Then
Awesome.
see you back in 5 minutes.
Yeah, yeah. Cheers. Catch you now.
Hey,
Isaac. Cool. We're back. Back on.
all right.
Yeah.
Um,
Good catch there. Brilliant. That was really cool.
yeah, thanks for making me. Thanks for helping us step through it again. Um,
Yeah. Hey,
I know I didn't
anytime.
want to.
Yeah. No problem. Shall we step through it again? Uh,
Yes,
we're
let's
gonna
do it.
just, yeah. I've been wondering like how this works. We're always decrementing the keynode. How does that interact with whether we are ascending or descending?
Yeah, so ascending is a bit different here because we're now comparing key max with key min. So maybe it's
Mm,
best to like draw that one out. It's a little bit tricky.
yeah,
Um,
yeah,
undo all these things. I think I want to go back to red. That's what we usually use for searching. So,
yeah.
um, say we pass the key max into this function, but then when we compare against the key nodes, we compare with the key min. And so say our key
Mm,
max is actually like here.
mm,
That would be where we want to start iterating this direction.
mm.
And so what's going to happen is we're going to compare um, our key max with the key mins here, um, and then we're going to end up here
Yeah,
because we then go like one past this key min because it doesn't exactly match any of these key mins. Then we want to subtract one here to actually get to here actually, and then we go and search inside this range. So then we search all the keys in here. Um, we find the matching key, or we find maybe the matching key here, um, or we find like one less than the matching key here, or something like that.
yeah,
Does that make sense?
yeah.
Because
Cool.
there are
So
now,
we,
because the first this step just determines which key node we want to search inside, and we want to search inside this key node here, right?
yeah,
And so we always want to subtract one to make sure to get the key node we want to search inside. That's where our
yeah,
key could be. If we didn't subtract one, we'd be searching inside this key node, which would be wrong.
yeah. So for descending, we're passing in key max. Where the purple line is, that's the key min. So we know that key min of that purple key node is greater than our key max. So we jump
Yep.
to a key node to
Yep.
the left. Uh,
Yeah. And then we now compare to make sure that this key min is actually less than this key min, and keep jumping to the
yeah,
left until we find a key min that's actually.
yeah,
Um, we can actually
yeah,
do an assertion here that if they're not equal, we can here assert that there's less than. Oh, well, we can't because there might be 0. So that would be then awkward. Let's not do that, I guess. Um,
yeah,
yeah. Are we on the same page there now?
yeah. Oh, that's cool. Okay, great. Shall we take a look at that code?
Sure.
Shall we finish stepping it through in the ascending direction and then we go through in the
Sure.
descending
And then come
direction?
back when we're descending. Sure.
Mm,
So we're now still ascending. Now we've gotten to the key node um, that probably contains our thing. So say
yeah,
again that our key we're searching for is here. It also happens to be, well, it's not actually there, but say like the key we happen to be searching for is the red one, but it's or say that like, this key is just like slightly less than the key we're searching for, and the key we're searching for is not exactly in one of these table infos. It's not
yeah,
the exact min key of one of these table infos, but it is contained in one of these tables. And so we want to find the table with the min key, just the greatest min key that's less than our min key we're searching for. Um, and so it's also here then duplicated in the key node. Um, and so we've now gotten to this key node min key. And
okay,
now we're going to search inside this key node essentially.
yeah,
And so we get the keys for the key node, and then we do a binary search on the keys looking for our min key. This now gives us a keys result. We assert that it's not equal to 0. We can do this because we've checked for an exact result here.
yeah,
If we get an exact match during the root search, oh, yeah, so this is correct. It might be slower. We're not gonna change any code here. I'm just gonna show you that we could do an optimization for the super unlikely case where this is the case. Um,
Yeah.
because right now what we do is if we get an exact match here,
Yeah.
and then it turns out this one also has the same key, min key, we're going to iterate over every key in this key node to get there, and then maybe
Yeah.
iterate a bit, then maybe then we'll jump to this one.
Yeah.
Um, we'll
Yeah.
probably end up like somewhere in here and end up going to that one, but that's
Mm.
fine. It's an optimization. It would be a pointless optimization because we'll never hit that case in practice. Um,
Yeah, it'll make the common case slower if we do that. It'll make the rare case
Indeed, and we don't
faster.
want to do
Make the
that.
Yeah, yeah. Cool.
So
I was thinking
forget
what
that.
we should do. No, great idea. It's cool, like that we know we've explored it. I thought maybe
Yeah,
this comment we've got in the rather unlikely event. There's kind of two things. We should move this comment to be just above the while loop, and then where we actually do root result dot index minus one, I think we need to make a comment to motivate why we don't.
yeah,
I think someone else might look at this loop and say, why don't you just always do the minus one in the while loop, or can't we rewrite
yeah,
it? Or
sure. We definitely
so
should justify that. So
I think we need to
yeah, just
motivate that
um,
this is also something that's necessary.
turns the
Yeah.
next um, greatest, or the index of the next greatest item, index of the next greatest, uh, next larger key of the
Yeah.
of the
Of
first first larger key in if since there is not an exact match,
Yeah.
since there was not an exact match, the binary
Binary
search
search.
returns the index of the um,
We're just
immediately.
missing. Yeah. After returns, we've skipped the returns the index.
Is that the right? I don't like this wording. First larger key
Yeah.
sounds weird. Um, the first part seems good to me though. Um,
It's the returns the index of the key. The I had a way of saying it, but I don't know if it was a good way. But it's the smallest index of the key that's great. It's the smallest key that's greater than the target key. The smallest key that's greater than the target key.
yeah. Um, yeah. The
Or
lowest
it's
upper
the
bound.
it's
So it's like
yeah,
the lowest upper bound, but we want a lower
yeah.
bound.
Yeah,
Um,
or we could say another way of saying it just as an option, like maybe the upper bound is a good way, but we could say it returns the index of the next greatest key.
yeah, that's actually good.
Key.
Key. We, however, we need a lower bound here, however. So subtract one.
And that's especially for an ascending iteration. Otherwise, we
For
would be
both. Yeah,
incorrect
we could be
for
wrong in
both.
both cases if we didn't do that.
Okay.
Well, actually, I think you're right that so say we didn't do that for a descending iteration. I just want to explore what happens. So our key
Hmm.
is here. That would end up getting us to here, and then yeah, we'd actually get this. No, I think we just yeah, we think we get this right, but it'd just be really slow. Um, because I think we'd iterate in this whole we'd just start iterating. And, well, we'd
Yeah.
actually skip stuff though. That would be wrong. We get this wrong as well.
Yeah.
Okay. Or we'd return stuff
May-
we're not supposed to return is what would happen. Um,
Yeah.
cool.
Yeah. Um, Maybe we could just make the comment a bit stronger and say for correctness, we must subtract 1 so that we do our binary search in the correct, or well, we must therefore subtract 1 so that we perform our binary
Yeah.
search in the
Let's
correct Keynote.
therefore subtract 1.
So that we perform the binary search.
Next.
Yeah.
In the Keynote that may contain our key.
Yeah.
Yeah. Which may key. I think I just do it like that to make sure it's clear we're referring to the variable key.
Okay. Cool.
Yeah.
And then for perform, we've got the R and the E swapped around.
Yeah.
Yeah. There we go.
Perform. Ooh, sufficient is also spelled wrong.
Oh yeah, I spotted that and I didn't want to interrupt your flow, so I was going to mention it and then I forgot about it. And while we were doing this comment, I
Spell
realized,
check
oh,
cut though.
yeah, cool.
All right. So, I think we're happy with this now though for ascending, which is what we're looking at now. Then we do our binary search on keys, and we get either an exact match or the next greatest key. We can assert that the result is not 0 because otherwise we would have hit this branch.
Okay.
Because yeah, and then it can't be outbound to the left, because we have the early return here. So it can't either. These are the two cases where it would be 0. We've now made it impossible to actually get 0.
Okay.
And so we're
And
good
just a
with that.
question.
Then we do our adjustment.
How does that, our assertion, how does that interact with our new while loop that we've added? It's still correct. Just to double check
Yes,
that it
that's still
hasn't.
correct. This is asserting on keys result index, not root result.
Yeah. Yeah. It can never be 0 because we can never match on the min key.
Exactly.
Otherwise, we would have had an exact match. Yeah.
So there's two cases where it'd be 0. Either we've matched the min key, or we ended up with something out of bounds to the left in the first key node.
Yeah. Okay. Perfect.
But both cases we've handled here. Here. So I'm very confident in this assert. And if it fails, it'll be very interesting. So I'm also looking forward to whatever that happens, if it happens ever.
We'll learn something. Yeah. Then it's just liveness.
We'll learn something
very. Yeah.
Yeah, it's just liveness.
Yeah.
All right. And then here we do the trickiness where we subtract if it's not an exact match. That's the last tricky thing here.
Yeah.
And this is to, oh, you know what? Yeah, we got, no, we're fine here. This is okay. Or is it okay? It's not gonna, no, this is not okay. We need to do the iteration here as well, don't we?
Yeah. Exactly.
Yeah. This is actually going to happen in practice too.
Yeah. Good.
Now we're looking at the case. Yeah. So things just got trickier. So let's have a new diagram or something. So now we're looking at like the blown up version of like one little bit of this. Is this like good enough?
Yeah.
Now we're just like looking at a smaller bit. We're only looking at the second binary search, and we've got like several keys that are the same. I'll make like several purple keys here.
Isaac, can we, our two segmented arrays, can we just label them? Are we looking at like top one is keys and bottom one is tables, right? Yeah.
Indeed. And let me like label them real quick.
Thanks.
Keys. Tables. I like this program. It's pretty neat.
Yeah, it's great.
All right. I think that's enough of that one, and then we're gonna have some blue ones here. Or actually, maybe I'll choose a more different color. Is orange good, well visible? I think it is.
Yeah,
Yeah.
yeah,
Have you already seen this, or am I explaining it to you too?
yeah. I've seen it because it corresponds to what we do in keys with where the -1 isn't
Yeah.
enough, where you've got
And
tables that
so
share the same.
essentially, this case is where we don't find an exact match, um, and the binary search then gives us like, well, can this happen actually? Maybe this can't
Um,
happen. Can the
so
binary search
we,
give us one of these? If we don't find an exact match, can the binary search give us this? Say say our actual key is between orange and purple. Say the actual key is here.
yeah, it's
Can the
gonna
binary search give us?
return.
Does it have to give us this orange one, or can it give us one of the higher orange ones if all the orange ones are the same key?
I think it'll keep subdividing the space. It's gonna return the smallest, the smallest, the index. Yeah, it'll literally keep going left until it stops. It's subdivided the space fully, and then
So
return that
maybe we're
element.
fine then.
Mm,
If it always returns us the first orange one, then we're fine. But
mm,
if there's a chance it could return us one of the other orange ones that are not the first orange one, then we've got a problem. Because then we would
yeah,
subtract one and still have an orange one, and then skip data here. So this is more of a question of how our binary search works than anything else, I guess. I think
yeah,
we should add some binary search tests with duplicate keys and see what happens.
yeah. I
Um,
think so. Yeah. I'm also wondering, like,
or
for this
I'll just look at
section
the
of
code.
code, if we can think of a way to tweak the design so that we don't get into this territory, that we can move our maxima so that we're in a safer place, that it gets. I'm not sure if we can. I'm just wondering, like,
Yeah, I think we can't really. Um, it's just thinking about how the duplicate keys mess us up. Um, or
yeah, I'm happy. I think the idea that we have of thinking of it as an array of tables, and we want to put all the tables in the same array for the level. I think that makes sense. Like that,
yeah,
that's the right, to me, that feels intuitive, that you've got some, that you've even got duplicates in there. I'm just wondering if how we write the code, maybe like using the bool to int, maybe it's too tricky, or I'm
I
just
think the bool
asking the
to it's
question.
fine if it's correct, if the
Yeah,
logic's correct. I think it's the tricky
yeah,
part is getting the logic right. I think how
yeah,
the code's written isn't having a huge detriment to the logic, I don't think.
yeah, yeah. Like if
Um,
we broke it up at the high level into multiple methods, or just change things so that it just gets easier, if it could get easier. I'm just wondering.
yeah, I'm not sure. I'm not sure it can get easier, to be honest. I think it's just tricky stuff we're doing.
Yeah.
Um,
Okay.
there's kind of
Okay,
like
cool.
implementing custom data structure essentially that's got to
Yeah.
have very specific characteristics and deal with a lot of data. And so I think
Yeah.
it's just going to be hard. Um,
Yeah. So what I mean is, if we can take this hardness and abstract it somehow in, maybe slice
yeah,
it up into multiple methods, or that
I
would be
think
probably the only thing we
making out a
could do.
segmented array definitely helps, but I think here
Yeah.
there's not much. I don't think abstracting it more would help in this specific case.
Yeah.
Um, I can't
Cool.
really say in general. It's kind of hard to say
Yeah.
in general. But for this
Okay.
specific case, I don't think it will help us at all.
No.
Um, I think what we need to do is look at our binary search to see what behavior it actually has. If it will
Yeah.
always give us the first orange one here in this example, or if it might give us the third orange one, or the second, or the fourth.
Yeah.
I think it might
It,
actually always give us the first one, in which case our -1 is fine.
yeah.
Um,
It will, because it'll see that the key is greater than what we're searching for, so it'll subdivide the space to the left. It'll
yeah,
move
I think it
left.
will always give. Yeah, I think you're right. It's only when an exact match will then like have the short circuit Or maybe
Yeah.
just because it's branchless, does it actually always go to the left in the case of an exact match too? Um,
Uh, that's a good
no, it
question.
wouldn't. I don't think. Okay, so yeah, maybe it would. We'll see. Because I think what happens there is that no, I think it wouldn't. Because I think what happens there is that we then um, have length one when we get an exact match. Maybe not. Okay, we should just step through this on some example arrays. Well, let's just first do some test cases. That's the easiest way
And then we've got it
to
permanent,
introspect
perm
this.
permanently documented also, you know?
Yeah. Um, with duplicates.
Mm. Or just duplicates.
Yeah. Okay, so our search array, we're gonna have we have like a zero still. You
Mm.
have two zeros, three ones, and maybe have some space between them, like should be three threes,
Yeah. And then four fours.
four fours, five fives. Keep on going.
Yeah. Yeah. Yeah.
I think that's enough to be honest for this test.
Okay.
Um, 0, 1, 2, 3, 4, 5. I think just going up to 5 is enough for our purposes too.
Yeah.
And then let's see what we get out. So what do we hope to get out? Let's just like go for that first. Um, I hope to get out the first three and the first four. Well, no, for one, I would expect to get out the first three. For two, it would also be the first three. Oh, this needs to be index one though.
Indexes. Yeah.
And okay, and then for three, I also expect to get out the first three. Index. Oh, these are index two actually, because we've got two zeros in there. Um, and then we've got index 0, 1, 2, 3, 4, 5 for the fours. And then 5 would be index 6, 7, 8, 9 out of bounds.
Can we line it up quickly, just temporarily? Shift the middle array just two spaces to the right, just so we can see how the needle
The
and the
middle.
result line up. Cool.
You mean
Maybe
this
all of them,
one?
yeah. Yeah, and the middle one as well. So you can see, okay, so we search for zero, we're going to
Okay,
get
I see.
zero. Yeah. Search for zero, we're going to get zero. Search for one, we're going to get two. Search for two, we're going to get two. Search for three, we're going to get two. Um, search for,
Actually,
maybe,
I want to test something
uh,
else here actually. I want to
yeah,
make this 5 and search
yeah,
for a 4. Um,
yeah,
and then I want to get 5 there, and I also want to get 5 here, and then I want to have a 6 where
yeah,
we get 9.
yeah,
Oops, I messed this up again. Can't stop myself from zig formatting like right away.
yeah. You see, this is tricky because the search, if we get an exact match, then it technically can return any one of the fives for us. That's okay.
Are we sure about that?
Yeah.
I'm not actually sure that's the case. I was looking at this, and I'm not sure that's the case. So, because we
Yeah.
always do the same number of divisions, because we never like jump ahead in the divisions. We always divide by 2 every time. So we always do the same number of
Mm,
iterations.
mm,
Um, maybe we stop moving the cursor, I guess, once we get an exact match. So we'll
yeah.
then never return less than. Um,
It
so this will
starts.
always return false then, and
Mm,
so we'll then take offset. And offset will then just remain the same. Okay. Yes, we'll
uh,
stop moving the cursor once we find an exact match. You're right. So it won't
yeah.
be deterministic which one we get there.
I
But
think it
um,
my gut feeling is that it starts to depend on the actual runtime data. How you, um,
yeah, it depends on
the
how
width.
you divide or how well it divides
Yeah.
into two. I think we can actually predict it if you want to try. How many things do we have in
We
here? We got one, two, three, four, five, six, seven, eight, 9 things. So 9
yeah.
divided by 2 is 4. 4. So the first one we're going to do is look at the fourth item, which is this one. So we're searching for a 3. I think we're going to get this index. I think it's going to be index 0, 1, 2, 3 here, actually. And when we search for the 5, we're going to look at this one first, 9 divided by 2. Then we're going to say, okay, that wasn't right. Let's look at the rest of these. Let's take 5 divided by 2, which will give us, I think this will be the first one, actually. Yeah.
I think when we search for 3, we're actually going to get 4 as our index, because 9 divided by 2 is 4. Oh, do we do a -1 somewhere?
I was thinking we did, but I could be wrong.
Yeah.
No, it's just length divided by 2.
Okay.
9 divided by 2 is 4, and then we have half and off. Yeah, you're right. So it will be 4 as the index then.
For 3, yeah.
I messed up my, yeah, and then this should probably be 6.
Yeah.
So we'll get then, we'll end up with this one, I guess. That is the middle element in this array, yeah. And then
Yeah.
this one, I think it'll give us this one, so it'll be 6. Okay, let's test this and see what happens.
Yeah. I think we can rely on it. If it's an inexact match, we can rely on the binary search returning the smallest element that's greater than. That we can rely on. But if we're trying to search where the needle is going to get an exact match and there's duplicates, then I think all bets are off. We shouldn't depend on the implementation to. We should just expect that it's going to give
okay.
us. We should just expect that it's going to give us one of the exact matches, any of the indexes. I don't think we should require the binary search to give us a specific index for an exact match.
Yeah.
We should only.
Format? Sorry, I'm distracted by
Okay.
something
Okay,
else.
cool.
Just the compilers.
No
I
worries.
got confused. I think our zig format, like, to remove the Qualcomm inline,
Yeah.
isn't good. Oh, say,
No.
do I have?
I use
No,
0.9.
it didn't.
Okay.
I want to test because now it said expecting. Yeah, so calling convention mismatch found definitely call count inline. Okay.
I think it's where we pass
inline?
we pass a
this, I think.
callback. Yeah.
What now? Now it works. Okay, we've had a failure too. Expected 4 found 2. Interesting. That means it did find the first 3.
Yeah.
0, 1, 2. So.
It's because it keeps running. So the first answer is 4. It's branchless, so it keeps running. So it gets 4.
Yeah, that's what I was saying. And then
it divides 4.
Again.
Yeah.
Then it subtracts from length. Length equals half. Okay. Yeah. But then. Okay. But so it then changes mid, but it never selects mid, doesn't it? So it hits if it hits the exact match once, then oh well it will hit maybe perhaps another non-exact match, or no, it won't. I use mid offset.
It's either going to select offset or mid.
I'm going to keep testing it empirically to see what it does. Expected 6 found 5. So 0,
we can work
1,
it
2,
out.
3, 4, 5. Yeah. So it did actually give us the first thing here. I think we should add this to our fuzz test and then just say it works.
Yeah, But the thing is, I would say that we shouldn't spec the interface so closely. Like, what is that?
I think we
It's called
should.
hero. It's called. Okay, well, yeah.
I
It's
think we
kind of
have
like
this binary search. It does what we want, and so why not use it? Um,
yeah. The reason why is because then it ties us down to the implementation too much, like Hiram's law. So and elsewhere where we're using binary
yeah.
search, I think it's okay if we depend on the property that if there's no exact match, it'll get the smallest element that's greater. That's because that's how binary search works. It keeps dividing the search space and then stops
Okay.
till
Yeah.
there's no more elements. But if it's an exact match, we should maybe the binary search does work this way, but we shouldn't depend on that because that's a lower bar for correctness. Because otherwise we start to depend too much on um, but maybe this is just how binary search works. If it's, but you see,
Yeah. You know what? It wouldn't actually help
for
us though in this case.
yeah,
Um,
yeah. I just think we
so
shouldn't depend on it externally, like outside of binary search, because it's making the bar for correctness too high. Because for example,
yeah.
if binary search was branchy, if the implementation was branchy,
Yeah. Yeah.
it
Then it
would
would
it would
return
re
early.
yeah,
I
yeah,
think you're. I think I. Yeah. I think it's a good point. I also think on a higher level or a more specific level, it wouldn't help us to depend on this behavior in our case here
yeah,
because um, you still have the case. You still have to iterate because there's the case where, or maybe not. Yeah, because then you end up with an exact match on one of these boundaries. We still have to have the function that does the iteration, because you still
yeah,
have to handle having or matching exactly this, but then looking in the previous node to see if it's there or there or there.
yeah, yeah.
Um, but this definitely makes me like this now. This behavior is very good. I think
Yeah.
I'm happy with that. So it also seems to work perfectly here. So should we just add this to the fuzz test and then, or how
Yeah,
about do you add this to the fuzz test?
I don't think we need to fuzz it. The If we go down to the that unit test we've got, I think we should just change it that we don't search for exact matches there. So we search for things that aren't there, and then we should expect that we get the smallest element that's greater. That's what the test
Okay.
should document. And then
So
anything
stop
else
searching for
is
three, stop searching for
yeah,
zero, and stop
yeah,
searching for five. And then we're going to search
yep,
for ones. Expect to, let me line this up again. So for one, we
cool.
expect to get
One,
two. For three, for two, we expect to get
two,
two. For
yeah.
four, we expect to get five. For six, we expect to get nine.
Nine, nine. Yeah,
Is that
cool.
good?
Yeah, okay. And then what we're saying is the anything else is undefined, and that leaves the implementation free to be branchy or branchless. Because
Cool.
branchy can be good where your binary search is over big data. That then when it gets very big, it can help to be branchy. So
Interesting.
yeah,
Okay, yeah, because
then
then
we
you have a or a fast path if you get lucky, I guess. Um,
exactly. Yeah, and then we're also free to have a switch internally that we decide on which, but I'm not that we would ever want to do that, but yeah, cool. But
okay,
this is
cool.
this unit test is important because we do expect this to be the case.
Yeah,
So no,
definitely.
yeah,
Yeah, or say I should actually just leave a comment here and say our well implementation requires that if there are duplicates, um, there are duplicates. How do we formulate this properly? If like the next greatest key has duplicates, the first the first key that
yeah,
the very first key in the array that in the case of an index that if the key is not found, the index of the very first key in the array,
the next greatest index of the next greatest key, even in the presence of duplicates. The index of the next greatest key.
Index of the
next greatest key, even in the presence of duplicates. Duplicates.
Did I spell that right? I did not.
Almost. That's it. Nice. Do you think we should pop this test actually into manifest level rather? Have it there, because that's where we
because we test the binary search there, don't we? Then we have to like copy the search infrastructure as well.
No, let's leave it. This is good. Cool.
And so I'm happy with this boolean now, because that's correct now.
Yeah.
So now what's going to happen is get rid of the red stuff. So our binary search, if we have this case where we're searching for something in the middle here, it's always going to give us this key. And we're searching for a purple one, it'll give us one of the purple keys at random. At least that's what we're saying. It'll actually always give us the first one. It's actually nice for performance reasons, because then we'd have probably less iterating to do. It's only the case where it's spanning across a Keynote boundary where we then have to iterate more than one iteration to see that we're done.
But we don't.
But we don't rely on the behavior. Exactly.
Exactly. Yeah. Cool. Okay, so we find, so it's an inexact match. We will get the first one to the right, not,
Yep. Cool.
And then, are we then correct? So for ascending direction, we're going, if it's inexact, if it's exact, it's not going to be at index 0. It's going to be somewhere else. So we're setting relative index to the index minus. Oh, okay. So this is it. If it's an inexact match, then we want to subtract 1 for the same reason we do when we subtract from the root.
Yep, exactly. If it's not an exact match, we need to go to the left, because then there's the chance that the max key of the table to the left, which we haven't looked at, is greater than our min key we're searching for, or the max key we're searching for, in the case of a descending search. So I think we've now finished this for the ascending direction. Do you want to look at it for descending one more time as well?
Yeah. If we can just, before we do, if you can just help me to understand, I'm a bit groggy on I understand at the root node, we only have key mins in the root, and we only have the key min of a whole key node. So, and if it's inexact match, it's the key node to the right that can't possibly contain it. So we want to go one left to where we might. But for keys, there we've got key mins, and we've got a whole lot of key mins. If
the same principle though, because we don't have, because we have then tables below the key mins, just like we have got key nodes below the root nodes. And so the key mins we see in this keys array only tell us the key min of an entire table where there could be, where a key could also lie if it's not exact match of the key min.
So for correctness, we have to go one to the left, because the previous table might contain the key range. Okay.
Exactly. Shall we That's what I was saying about the key max of the previous table could be then greater than the key min we're searching for.
Okay. Shall we document it, Isaac, over here?
Like explain why we do the -1? Yeah, we probably should.
Yeah. I'm just switching on the AC quick. I'll be back. Yeah.
Cool. I'm gonna put this on a new line. I think I want to take it out of this function call just to make the document a little bit nicer. So I'm just leave here const relative index equals. This is one way to make the code just more readable, so do less things at once. I think that's one
Yeah.
thing we can strive to do. I think the
Yeah.
bool to int though doesn't actually make it less readable though, as long
No.
as we explain it well with a comment right before it happens.
Yeah.
Um, the alternative would be
Cool.
an if statement, which I think is less readable actually.
Yeah.
Um,
Yeah.
so, how do we explain this again? Well, we can kind of copy like this explanation. And next, greatest key. However, um, or well, let's keep that. We must therefore subtract one.
To It's got to do with
As
table key
is
min and table
possible
key max.
for
The
the
previous table.
previous tables
Key
to
max.
contain a
Yeah.
that is the key max of the previous table could be greater than key. How's that?
Yeah, that's cool. And it could be that there is an exact match here, which is why we use bool to int.
Yeah. Oh yeah. So in the case of an inexact match.
Yeah.
An inexact match. And then do we explain this? We need to explain why we have this function. um,
Yeah. Yeah, we should. But if we go back just up again, I'm wondering, so if we're thinking of ascending order, then
yes.
we want to go back to the left. This is to the left from your perspective? Hey, so
Yeah.
flip it around.
Good.
Okay, cool. Yeah, so if we're ascending order, we want to go to the left because it could contain it. Um, okay, that makes sense. If it's an exact match, we still need to fix it up with the start boundary.
Indeed. But we don't do the
And
subtraction here.
exactly. Okay, and then when we call start boundary, we just need to pass the direction, I think,
Yeah, and
in
also in
addition.
the case of an inexact match, we need to fix up the result of the subtraction with the start boundary. Because if we, so say the binary search will give us, if we're again searching for this position, like a key between these two keys, binary search
Yeah,
will give us this key, right? And then we'll subtract one to get this key. But that might not be the earliest snapshot. We might actually want this one because the snapshot, that's the visible snapshot for this current query.
yeah, yeah, yeah.
So we still need to fix it up there. Our code does that correctly. I just want to point that out real quick. Um,
Cool, cool.
there's not this in
Thanks.
the other case. It's not only in the
Yeah,
case of an exact match that we need to fix up.
yeah.
Um,
We always need to fix up. Yeah.
yeah,
And if we're doing descending order, then we're also going to get the thing that's greater than. It's inexact, so we're going to go one less left. Have we got a bug there? Where we're going to actually then cut the descending iteration
so
short because
in
we're going to
descending
go one
order,
left. We're going to do -1 here.
I think that's fine. Um, so in descending order, we're searching based on the key max. Um, and so we see that, so here, say if if we're the key max we are searching for lies between this key min and this key min. These are all key mins, these lines here, but the key we're searching for is a key max of our query range. And so we see that our key max is less than this key min,
Yeah.
so we don't need to look at that table. Then we subtract one to look at this, and then
Okay, that's cool.
this is now the table we restart. And so It could be that our key max is also less than the key min of this table. No, it can't be because the binary search would have returned something else then. So
Yeah,
we then have
cool.
to assume could be that so our key max is then likely or that will then must overlap with this table with this table that's in purple, and we'll
Yeah,
have to just find the right snapshot version to look at then.
okay.
Um,
And
we good
here,
there?
if yeah, we're good. Here, these are now the key mins of tables, so we're not at the root anymore. So if I'm
Yes.
correct, for descending iteration, the subtraction of one is not actually required here for correctness.
Um,
Although actually it is, because we've decided we want our iterators to return the tightest bounds. We
yeah.
don't want them to cut the iteration short, and we don't want them to
Yeah.
return superfluous data if they know they shouldn't.
We want to
Um,
look only at the tables that overlap with our query range, and so this is
yeah,
necessary. Yeah.
yeah, okay,
Cool. So now our iterator should
thanks.
always return a table that overlaps with the query range, I think. Um,
Yeah,
or always
and
start
it's
with a table that is in our valid query range. That's good. That makes our iterator simpler by a lot. And we can also assert that now when we create the iterator, I think. Which we should probably
yeah.
add. I don't think we're doing that right now.
No,
Um,
it can't be sure on the key max side, but it can be sure on the key min side.
yes, that's right. So hmm, maybe we can't actually assert anything there, but
We could assert the
it
key
could
min
always,
side.
it could,
No.
so I think it's like either an empty iterator or it overlaps
Mhm.
with our query range.
Yeah, yeah,
Because for ascending, if you if we like if we don't find an exact match for the key min, we'll go to the previous key min, and then if the key max is also out of range for our iteration, so the key min would then be greater than would then be less than our key min. The key max is also less than our key min.
yeah,
Then we have to go to the next table.
yeah. So I think we
But
could
then
do
we
the
already have looked
assert.
at that table to see that it's out of range because it was
Yeah,
the key min was greater than our key min.
yeah.
Hmm. I just lost myself there. Um,
Sorry,
I'm
I
gonna need to go
interrupted.
look at this stuff again.
Yeah, yeah. I think what we can do is after what we get from this, after fixing this stuff up and that, I think we can assert that according to direction on the anything on the key min side that we can assert for the range. When it comes to key max, we're not sure because our structure only has the key mins in the root and the keynotes.
Yeah,
But we should be able to do the
that sounds
assertion
right.
for one of the.
Yeah, I think there's a few more cases. Let's not get ahead of
Yeah.
ourselves. Let's finish working through this for descending order, I guess.
Yep.
So here, I think we did this for descending order already today. I think we're happy with that,
Yeah.
right? Um,
Yeah.
then here we do the same binary search on keys. This still holds. There's no exact match, and so we, in the case of it can't, if it's out of its left, we just return null.
Yeah.
Um, yeah. And
And
so
Isaac, just a question.
yes,
Do you think it makes sense for like descending iteration? You know how we swapped that we've got this concept of key, which is either key min or key max. Does it help us if we just use key min always so that it's easier to reason about?
we can't do that. Um,
Yeah.
we won't be able to find the right place to start descent for descending iteration.
Yeah. Okay. No,
So,
I also thought so. Just wanted to throw it out.
so yeah. So if we looked at the key min, so the iteration always like covers a range, right? So it'd be something like
Yeah.
this to this. The key
Yeah.
min
So
that
we,
for sending iteration bounds is this. But we
yeah.
can't start there. We need to start this end and iterate this way.
Yeah, exactly.
It just wouldn't make any sense to do that.
No,
Um,
no. Okay. Dumb idea. Sorry.
No worries, I had them too.
Yeah. No problem. What do you think? Is it time? Maybe we could do a lunch break now for 45.
I think I could use a lunch break, yeah.
Yeah.
We do 45 minutes again. Um,
Yeah. And when we come back, we just quickly run through the descending again, and then we're out to where we were
yeah,
at. Yeah.
sounds good. So see you back at 12:30 or half past, I guess.
Half past. Yeah.
11:30 for you, 12:30 for me, I guess.
Yeah. Yeah.
10:30
I'm actually.
UTC.
Yeah, exactly. I'm ahead of you,
Or
so
you're
it'll be
13:30.
one. Yeah, 13:30, and you're 12:30, right? Yeah.
All right,
Okay.
cool.
Happy lunch. Yeah. Catch you now.
Cool. See you in 45 minutes.
Cool.
So you want there's going to be no
Hey, Isaac, and we're back. Oops, I think your audio isn't coming through. It's got the squeak again. Maybe let me try and just rejoin the call. Let's see. Device. Testing. You want to try now, Isaac? Now you should be coming through, but I don't hear you.
Testing. Are we good?
Now it's
Can
coming.
you hear me?
I can hear you.
Testing. It's turning green on my screen, like the border around my frame. Cool.
Yeah.
All right, we ready to go then?
Yeah, awesome.
All right. So yeah, when we left off, we were just about to like re-examine this for. I think we already kind of made it through to examining this for descending again.
Yeah. I'm getting a tiny bit of feedback on my side.
Sorry, I'll turn down your volume a little bit. Hopefully It's better now.
Okay.
So we'll move the mic a bit further away from the speakers, closer to me. Okay.
Awesome, thanks. That's perfect. Yeah.
Cool. Excuse me. All right. So for the descending search, we've verified this already, I believe.
Yeah.
We have the same strategy there, with the same cases where things would go wrong if we don't have this loop.
Yeah.
Then we do the same binary search on the keys as we do for ascending. This will give us then the first min key of the first table that we need to look at in our iteration, or at least that what we think is the first table. It may be, well, it'll give us the min key of the first table. That's correct, but it may not be the exact right index. We'll have to adjust that then with our iterator start boundary. And we also need to pass direction to this, don't we? So
yeah.
We should pass that.
Cool.
And just do it like that. Yeah, that seems better. All right. You have we can't be out of bounds. We already would have returned here or here. That's the same cases. I mean, the assertion is the same because there's no difference between the code in the path leading to this point for ascending or descending. For the assertion, it can definitely still be the same. And in the case of an exact match, the logic's the same here as well, because it's just like this, where we still need to do the same thing here. But we don't need the loop here. And why is that? Well, does that mean we don't need the loop here either? We already know there's not an exact match. Yeah, we don't need this loop anymore. If we say there's not an exact match, with our new binary search test that says if the target key is not found, if there's not an exact match, then the index of the next greatest key is returned even in the presence of duplicates.
Yeah.
It means we'll always get, if we're searching for 2, we'll always get the index of this 3, not the index of one of these 2 3s.
Okay.
And so we don't need the loop anymore.
And is that the case for the root node as well?
Yeah, it's the same binary search algorithm.
Yeah. 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 Okay. I think
that's nice.
Yeah.
And so an exact match, yeah, and so the exact match here is also fine, because that means that if we go back to our diagram, it means like we're searching on the root node, and so maybe we find this key is an exact match, but actually all the keys in this whole range have the same min, or these are all the same min key in this entire range.
Yeah.
We're just gonna, our iterator will just handle iterating back to this key and starting, and then going in the right direction.
Yeah.
That's fine.
Cool. Yeah, I agree. And
cool. So that actually gets rid of that loop then.
Yeah.
That's nice.
Can we check that?
Are you happy with that?
Yeah, I just want to read that loop quickly. We're comparing if it's the same. So at the moment we're saying if it's the same in exact match, but it can't be because we would have been all the way to the left. So
we're doing assertion then.
Yeah, we should.
Yeah.
Awesome. Great idea.
Yeah, we can copy this. Compare keys root keynode and root result index. So yeah. And we want to assert that this is a less than relationship. Yeah. Cool. I'm very happy with this now.
Awesome.
Because then we now assert that we don't need the loop, which is even better than not needing just fuzzily not needing the loop.
Exactly. Shall we leave some of that old comment that we had there though, and then just to explain why we have this assertion so that we remember it?
We just grab the comment back, then go back and delete this and fix this again. Equals less than.
And then we could leave the comment exactly as is and just add to it and say it isn't sufficient to get to the next lowest key min, comma, unless our binary search always guarantees to get to the next greatest key even in the presence of duplicates, comma, which it does. I don't know what you think of that. Guarantees the first E should be an A. A-N-T-E-S. To get to the next greatest key in the presence of duplicates.
I'm going to write something slightly different. You can tell me if you like it or not. To always return the immediate next greatest key. The C and
that's it. And then we can say
like immediate there.
Yeah, I like it. That's great. And then we could just add comma, which it does. It's kind of run-on sentence. Yeah.
That's one sentence here. In the rather likely event that simpler.
That's okay.
There's also no place you actually need commas here, because in a rather likely event that two more kids.
We should maybe have a comma before the unless, just to.
Dependent clause. Yeah, I think a comma here makes sense. It just sounds better.
Yeah.
I don't want to think about grammar rules right now.
No.
They're not even like. That's the thing about like human languages.
Yeah.
Rules are too flexible. It's not like a programming language where it's either compiles or doesn't.
Yeah. Exactly. Yeah. I always add extra commas just to make the clauses like crystal clear. And it's kind of like how one reads it, like pauses, you know.
Cool. We're good then.
Yeah, we could also just say unless, where we say unless the binary search, we could say unless our binary search. Yeah. Cool. That's awesome.
Cool. And I also made this const again because I've forgotten to do that before.
Nice.
All right.
I'm also like,
That
this
makes me much
is,
happier. I didn't like that loop.
yeah, yeah, yeah. Awesome, Isaac. Very cool.
It means there wasn't actually a bug there, as far as we know.
Oh, okay, yeah, yeah. No, we do. We've got our indexes correct in the assertion. Yeah, so there wasn't a bug.
Yeah.
But I mean, that's like a great case to have thought of,
But
you know? And
exactly. Yeah. We now
yeah,
got a very good assert out of this discussion, and
yeah,
we understand the problem much better.
yeah.
Um,
We're like,
yeah, definitely no wasted time there.
what we're kind
Um,
of exploring the surrounding terrain and getting
yeah.
shoring up our understanding, putting it in as
Indeed.
assertions. It's like the negative and positive space, not just does it work, but what are the limits? Yeah.
Cool. And now, so we should probably document. We need a document that guarantees that are upheld when by the return type of this function. I think.
Yeah.
I think that'd be very useful for our reasoning outside this function because it's a really complex code.
Yeah.
You don't want to come back to read this in like 2 years and try to figure out what the guarantees it's making.
No.
So we got to figure that out.
Yeah.
But also we'll clear up our reasoning in here. So, so given a I wonder if we should pass in both min key and max key here. Since we're passing in direction now, I think the better interface is to take both min key and max key and then do the key equals if direction, min key, or max key inside this thing.
Because it's otherwise, yeah, otherwise there could be like an interface mismatch, and then that's core to the whole.
Otherwise you can.
Everything falls apart.
Otherwise the user can screw this up. We don't want to allow them to do that.
No.
Yeah. We want to be nice to the user of this API and not allow them to screw up.
Yeah. That's because we fight for the users.
Oh yes.
And that's why this is also biodigital jazz. In the new Tron movie, Jeff Bridges makes this quote that he and Tron were cooking up biodigital jazz. Or no, I don't know. Yeah, he actually uses that phrase. It was like biodigital jazz, man. Something.
Awesome. I didn't realize that was where you were quoting it from.
Yeah.
I've seen that was the Tron Legacy movie. I've seen that. It had really cool music by Daft Punk.
Yeah.
That's what I mostly remember about it.
That's why I keep watching it again and again. It's just for the music. Like.
Yeah, that'd be fun to watch again sometime. All right. Root and key. Yeah, this looks good. Our switch. I think we do need to wrap this. I don't really know if we need to. Yeah, we definitely need to.
Cool.
It's 112. Looks good wrapped too. So, so this returns the place a valid cursor or just returns the cursor at which iteration should be started. This is the table
cursor.
Table array or table segmented array cursor.
Yeah, that's great.
Segmented array cursor, which iteration should be started. If there is, if may return null if there is nothing to iterate. If the key range is out of bounds. We
could say if there is nothing to iterate because the key range is disjoint.
Because the key range is disjoint with the stored in this level. Is that good?
Yeah.
I think with disjoint you need to say what's disjoint with.
We could also say is disjoint with the table ranges stored in this level.
With just the tables.
Yeah. Oh, that's cool.
Okay. So, there's one case that I want to examine closely here. So we've got this out of bounds case where we return null for descending iteration, where we know that we're out of bounds. I want to examine the other end of the case. So like being out of bounds to the right in the case of ascending iteration.
Yeah, which is where key min is greater than key max.
Yeah, but we don't have the key max of the table we're looking at. So I think we actually can't return null there at any time. That's kind of like, that's the other, because if we're looking at the last table in our whole level, we see the key min for that in our keys segmented array. We don't see the key max for that table. So we don't think we can actually return null from this function because we never look at table infos in this function. And so in that case, we will return the last key node and the relative index of the last key in that key node. And that'll be the last absolute index in the whole segmented array, essentially. And then we'll just rely on our iterator, which needs to then terminate immediately. Will either yield one table or no tables, depending on whether that key max is in range for our query or not. So that works out correctly then.
Yeah.
Cool.
We could, if we wanted to, because we've got the first half of the case here, we could handle the other case here just by checking which table node we're in. If we're in the last one, we can check and do the comparison and return null.
I don't think we can, at least not easily. I think we shouldn't either.
Okay.
It's already handled correctly by the current code, and I don't want to add like more special case that's not needed. I feel like that's just not idiomatic.
Yeah.
These special cases do good work because they allow us to do this assert here and simplify this a lot.
Yeah.
So it's never undefined behavior to subtract one here because we can do this as assert.
Okay.
And this assert's only possible with both of these special cases here.
Okay. Then what we could do is we could say in the documentation up top, we could say it will return. We could say may return null if the root if there are no tables. Because.
Yeah. That's why I say may instead of will here.
Okay. Okay, that's fine. Basically, we want to say that we examine whether it's disjoint based on key min only. The whole indexing structure only uses key min, not key max. So we return null if we know for sure, but we're not guaranteeing that it is disjoint. So yeah, it's good how you say may.
Only uses
so may
of tables.
But then that's the only
case.
It's only in the case where direction is ascending and where key min is greater than key max in the table. That's
actually not the only case we can end up with a null iterator. There's also the case where you have the same thing where you're in the middle. So maybe I can draw this out. So I'm gonna like draw out like a table, not even. So let's say we find this table.
Okay. Yeah.
And then, or the table is, so maybe I can also describe it in words better. I don't know. But it's the case where we don't get an exact match. We end up between purple and orange here. And then we go and look at the purple table. There's the case where the key max is also outside our range.
Yeah, that can happen really
it's
easily.
It's also less than key min.
Yeah.
And so that means that there's just no match.
Yeah.
And so that's not a special case then for the last element in the whole thing. It's the same case as for all the other ones.
Yeah. And it's actually the same case regardless of direction too. It's basically because our level manifest is actually, we should think of it as sparse. It's got lots of sparse ranges. So if the iterator range is in one of the gaps, well, it's going to get nothing out.
Yeah. Well, it could get nothing. It depends on like actually looking at the table info then.
Yeah.
But yeah.
Yeah.
Cool.
This iterator or iterator start will return a place, but it's actually up to the iterator to finally. Maybe we should just say that it's we could say may return null if there's nothing, because the key range is disjoint, and then we could say in brackets according to the indexing use of key min only. However, it's up to the outer iterator to check that ranges are.
I was going to say that note that the cursor returned is not guaranteed to be in range for the query.
Yeah.
As only the key min is checked.
Yeah.
As only the key min is
indexed
stored in index structures.
Yeah. Cool.
Therefore, I think that's enough. That says the guarantees of this function, and how the user handles this is up to them.
Yeah, I think we should just say instead of the note, we should say however, comma, the cursor returned is not guaranteed.
That works.
So it links up with what's gone before. And then
it is guaranteed to be in range in one direction though.
Yeah. Exactly.
Like in the direction of iteration.
Yeah.
Well, it's kind of tricky. I don't know how to state that.
Even there, it isn't, because it's sparse. So we could return a cursor not null, but we're somewhere in the middle.
Yeah.
I think what we've got is great. We could just, where we've got the however, we could add a comma after it.
All right.
However, comma, the cursor returned.
Yeah.
And what we could also do is where we say there is nothing to iterate because the key range is disjoint, we could just say instead, if there's nothing to iterate because we know for sure that the key range is disjoint.
Yeah.
So if we can know, then we try to know. If we can't know, we don't try.
Yeah.
And we could just say we know for sure that the key range is disjoint. For sure that. And then we could even, I don't know if you like, we don't have to, but right at the end, stored in the index structures, full stop, we could just add a comma, as only the key min is stored in the index structures. So we can't always know for sure. But I think that's overkill.
I think that's overkill, yeah.
Yeah.
Or we can be explicit here and say not the key max.
Yeah.
Sounds more clear, like only the key min. Is that not enough? Oh, it's not enough because you don't have the key max.
Yeah. Nice.
Cool.
Do you think we should do where we choose the key? We can maybe do that after we branch on how many root keys there are, because we can do that after we return null, because we don't actually use that up top there.
Sure. I was also just looking at
yeah.
Like this up here. Yeah, I guess we don't have to do it. So I just thought this function's become pretty trivial, but I think it's fine like that.
Yeah.
It just does conversion of this cursor into an iterator. That seems good.
So maybe what we need to be doing is this function should actually return. Well, no, we want it to be like this because it's going to make it easier to test.
Yeah, and it's also easier. It's also nice because we don't have to duplicate this code at every return, because this function's got 3 returns,
Yeah.
and 2 of them return like a different function. Actually,
Yeah.
it's got 4 returns now.
Yeah.
So we don't want to duplicate this code every return of the function.
No.
It's good like I think it's perfect like this, actually. This
Perfect.
is good.
Yeah.
And this is just more like a init thing that just copies these parameters into the iterator and then calls this function to find the start cursor and construct the other iterator.
Yeah.
Or construct it based on, so this is a good level of abstraction. This one only deals with like the business logic of figuring out the index.
Yeah.
And this one does like the boilerplate to construct the iterator.
And it makes sense that we do it there because that is the constructor function. Like that's where we return it.
Yeah.
So where we return it is where we should be creating it.
Yeah. Okay. And so I think we still need to look at this to make sure we're doing the right thing here. At least I want to look at there one more time.
It's
to make sure that we do return null right away if there's nothing to iterate.
Yeah.
And so this is the case where we didn't find an exact match, and so we return the absolute index of a table info where the key min is less than the key min of a range. We're looking at ascending for now. So we'll do descending in just a minute. So we know that the key min we're looking at is less than the key min stored here, or the key we're looking at. So that means that table info key min must be less than the key min we're storing here.
Less than or equal to.
That. Less than or equal. We can assert less than or equal to. Yeah. Let's add that assert back. I think we took it away because we thought we couldn't, but now we can. Yeah. Because we've now clarified what those guarantees are. And
I really like what we did under iterator start. I think it's really, really nice, and the constructor is great. Like the docs comments.
I think so too.
Yeah.
So I feel like we had this before and we deleted it at some point. I feel like we had this exact code before we went on break.
Yeah.
And now we check if we compare then the key min of the table info with the key max of our range. Why don't we look at the key max of the table info?
Because we have to... Oh, we don't look at that. We should be.
Yeah, I feel like we should be. I think we should be here comparing not key min of the table info, but key max of the table info. So we know that the key min of the table info
actually,
must be less than that.
I think we've got it right. So if we're iterating, we've got a table where the key min is 0, key max is 5, and our iterator has key min of 0, key max of 3.
Okay.
Then or our iterator has key max of 10. So we want to go further than this table. But I'm not explaining it well. I think, we need to type it out like this.
Should we like do it in numbers like this?
Yeah.
I'm having snapshots right now, so I'll like start a new one here, I guess.
Yeah.
Or just like start a new one entirely.
Cool. Nice. From food to bar.
Oh yes.
Yeah.
I should probably I need get like a notes directory set up that just like automatically, I can just like create new notes and then they get saved forever though, indexed by date or something.
That's
cool.
That's what I do. I've got a symlink, so in my Tiger Beetle project I can search for files, but it includes my notes directory, which is outside, and then all my notes are just text notes in my editor, and I name the note with ISO date format. So YYYYMMDD, and then I just put
right format.
whatever it is dot text, and then all my examples, like little counter examples for VSR, I've got a folder and it's all there, and then I just
Nice.
churn
I should
them
do
out.
that sounds nice.
Yeah.
But I want just a note command that I give a file name to, and then it prepends the date and puts it in the right place.
Exactly. Yeah. Cool. I must do that as well, actually. Yeah.
And then it would be also nice to have random store not just notes but random files. And so then I could also organize it by have directories for the year and the month, and then have just the date in the note name.
Yeah.
Something like that. I'm not sure how exactly that would work, but I think just having directories for each month would be nice, because then you can also stick temp files in there.
Yeah.
You're not sure if you'll need it again or not, because I use /temp for a lot of stuff, but then I'm always am I going to need this again at some point in the future?
Yeah.
Do I care if this gets deleted after a reboot or not? And then I'm not sure sometimes.
Yeah, and it's kind of cheaper just to always keep it, then you don't even worry about it, and you've always got it. So
seems like a good strategy.
Shall we do curlies, open curly, and then it's the min key, comma, and then it's the max key, and we can just put 0 and 10, 5.
Table 0 to 5.
Yeah.
Table
6.
6 to 10, something like that.
Yeah.
And say we're searching for key 4 to 4.
Yeah.
This is just interesting. I think it might be interesting to see the point lookup.
Yeah.
So our iterator is going to return us the index of this table.
Yeah.
Then we assert that this key is less than or equal to this key.
Yeah.
So that's good. It's the not equals to greater than here.
Yeah.
That's that assertion. Okay. Then this comparison says compare the key min to the key max for iteration. If it's equal to greater than, then we're done.
Yeah.
So we compare this to this. If it's equal to greater than, then we're done. That's good. But there's another case where we're done, where we don't want to return this table, which is if this had key max of 3. We don't handle this properly yet. And that right now we're going to return this table even though we shouldn't.
Of course.
You see?
Yeah, great. Good catch.
Cool. And so we now need a second condition else. So you're right. This is one valid condition for being done.
The other one is actually.
If we look at the second table.
The other one is actually whether we should skip. We need to know when we're done. That's one thing, and the other thing is whether we should skip tables and keep calling next on inner, make it a loop.
Yeah, that's right. Okay, yeah. Okay, so we do need that loop thing here then. I was hoping we didn't need that, but I think we just do because of the key. We don't have the key max. But I think we actually are done. I think we're done here, because we guarantee we return the greatest table that's less than the thing we're looking than the key min we query for when we're ascending.
But isn't it not because of snapshots also that we need to skip stuff in here?
Oh yeah. So we also need to skip because of snapshots. You're right. So we definitely need to skip because of snapshots in the first place.
Yeah.
We don't have that implemented at all yet. So that needs to happen here. So table info. So I think we first just grab the first table info, then we're gonna do a while loop to while.
Can't we even just do while it inner.next?
And then else return null.
Yeah.
That would work, yeah. So we can see const table info equals. Yeah, this is gonna be nicer like this. You're right.
Oh, I was actually thinking that we return from within the while loop. We continue, or we just return it straight from within the while loop.
Let me what I was thinking first.
Okay.
Then I'll write what you were thinking, and we can compare them.
Yeah, good.
Can't do both at once.
No.
Check keys, then break table info. That's what I'm thinking. Okay, what are you thinking?
So we don't use the while as an expression. We just say while. We don't even have const table info. Yeah, so just like that. And then we capture the table. Yeah, table info. And then if there's nothing else, return null. An else over there. And then inside here, we're going to have also our return nulls if we're done. Or sometimes we'll just have a continue if we want to just skip over. And so we'll have some logic.
We just like put the whole thing inside the loop body then?
Exactly, yeah.
Like just put all this inside the loop body? Okay.
Yeah.
That seems fine. Yeah, I guess mine was just it's pretty much the same control flow. It just kind of got rid of some indentation, but we don't really need to do that.
Yeah.
Yours
is cool too. If it works better, we do that. I just thought then we don't have to break and then still return. We just return when we return.
I did kind of like how we had the return null right at the beginning for this is better, I think.
Yeah.
So while we get table info, first to do is check if we need to check if the table info is like in the range from the left, like have we started, is it valid? But I think so. Let's go back a step real quick. Sorry, I'm undoing all this stuff real quick because I think we don't actually need this. Because I think we are done if we. I think in this case, if we compare against if we compare our min key, the min key we're searching for against the max key of the table we're looking at, we see that our min key is greater than the max key, we're done.
Yeah.
Because our start iterator function will never will give us this. If there was one where the min key was not greater than the max key here, or than the min key of another table, it would have given us that.
Yeah.
Tables can't overlap.
Yeah. I think what we should do is for level 0, I'm thinking we can actually solve level 0. Once we've got all of this stuff done, I think we'll find we can still handle level 0 if we just skip tables as we're going through. Everything should still work. Everything should still work. Because we only have key min duplicates.
Can we just talk about that when we're done with this?
Yeah.
I don't want to start thinking about that right now. I think it's a pretty big tangent, I think.
Okay.
I think it might not be as trivial as you think, but maybe it's doable. Well, let's examine that once we're done with this and have it working.
Yeah, so what I'm saying is that I think this solution of the while loop where you decide whether to continue for snapshots is the same way that we'll end up solving L0. So that maybe we wanted... but it's cool. I'm with you. Let's carry on here.
I'm really not thinking that we can do it that simply. I think there's going to be a lot of edge cases that we're not thinking of right now.
Okay.
But maybe I'm wrong. We'll see. We do need the while loop here for snapshots, though. So I'm going to put it back because we do need it there.
Yeah.
But we don't need to check the max key. We can just return the max key.
Yeah.
So
I'm with you.
Do the while loop first.
Yeah. So going back to what you were thinking, where we do want to check the max key when we're ascending. If the max key is before our key min, if the table key max is before our key min, then we're also done.
I can't write code and think at the same time, sorry. Shall I write the snapshot code first and then we can talk about that?
Yeah, I think don't do the snapshot code. Let's stick with what you were doing. So the that text example. Cool.
Okay, check snapshot or continue. Then we're going to go back here.
Yeah.
And this is then else Or we can just do like an or in here. Or compare keys, table info, key max, key min. Is that the right way? So we want to compare this. I've got this is my first thing in the compare keys color right now.
Yeah.
Then we want to check if that's less than
our key min.
Key min. Yeah.
Yeah.
And that's the right way to do bounds checking.
Yeah.
Because now we're checking both bounds, not just one bound.
Yeah.
And you also see the symmetry here, right? The key max, key min, key min.
Yeah.
That's symmetrical. That makes me happy now. We've got a solid balance check there.
Yeah.
And so
me too. I was always wondering why we're not checking like that we're within the table.
Yeah.
Yeah.
It also lines up really nicely. Look at that.
Yeah. Awesome. Cool. And then we can do the same for descending.
Yeah. That's right. Okay. Yep. So I was trying to figure out if we could do like an assertion here to double check our work, because I guess it'd be kind of hard to look at the next table. So let's not do that. I guess this is already good.
We could do like a
It's the same
debug.
checks for descending.
Yeah.
Is it really the same? Yeah, that makes sense. Okay, so we don't even need to differentiate between ascending and descending now. Or only for the asserts.
Okay. Yeah. Oh, nice.
Look at this. This is the same check as this. That makes sense too. We're checking for inbounds of the table.
Yeah. It's as simple
Yeah.
as that.
Cool.
Yeah.
Then we just need to add that assert for the descending,
Yeah.
because this assert is dependent whether we're ascending or descending.
Yeah.
And this descending is then it becomes not key min but key max of it.
I think we can't check it for descending because I think our iterator start doesn't give us that guarantee. It only gives it to us for ascending because of key min. Is that not?
Okay, let's think about this carefully. So for descending, we'll get some, say we're searching for this key, we'll get some table info. We don't get an exact match. That's when this assert's relevant. When we don't get an exact match. That means that we're going to get a table with a key min that's less than this key. That's the same assert, yeah.
So it's fine.
It's less than or equal to this key still. Except
Yeah.
this key we're searching for is our key max instead of our key min. So that's why I flipped it here.
Oh, okay.
So this is the same thing. This
Okay.
is what we're checking for inside. Yeah.
Okay. I must just get my head around it. We assert that it's not greater
Yeah.
than it. You see, if we look at our termination check, where we set done.
Right. It's a little bit weird, I agree.
Yeah.
But this does hold true. This is still double checking what we do in start iterator. Because this is not really related to this function. This is double checking start iterator. Maybe we should only do this in the first iteration. I'm not sure. Maybe we should I don't know. I'm not sure what we should do here.
So just so I can understand, we're checking that the key max of the iterator is less than the table key min. We want that to be less than or equal to our key max. Yeah, and iterator start does give us that because again that's key min.
Yeah, I think I realized we can't actually do this though because it's only true for the first iteration. Is that right?
Probably because otherwise it's our termination clause where we then stop.
Yeah, exactly.
Yeah. You see, it works for
So
ascending,
actually,
because in
I'm
ascending,
not sure we need this termination clause in if it's descending.
Oh yeah.
Because it's actually we get because we realized this at some point that like the way we work the way we do start iterator right now works better for descending than ascending. It's like a stronger guarantee.
Yeah. But I think it might come back to that idea of things are sparse, so we do still need to check it. Because the things where it's stronger for descending is only when you're out of bounds to the left. That's the only difference where we return null. But that only affects the far left hand side, not if you hit that case in sparseness somewhere in the middle. We should.
Yeah, so let's maybe query this for like.
We should work
well,
it
the
out.
same thing. If we've got like one even smaller, we've got like mine. I know we don't have many negative keys in real life, but I'm just gonna put them here for practice.
Yeah.
So, just to say we have got something more to iterate to on the left. We're still looking. We're starting at 4-4. Oh no, our range is now minus 3 to 4. Let's say that.
Okay.
And so we don't get a min key match, but our start iterator will return this table because that's the one that's immediately less than our max key.
Yeah.
And we do our comparisons based on max key in start iterator.
Sorry, Isaac.
We'll get this table out.
Just to add, so we're going to search for 4. We're going to end up with 6, 10. We're going to go one left because we do the -1 trick.
Yep.
So we'll end up there. Okay.
Yep. And then here, we're now starting our iteration. We can assert that 4 is greater than or equal to, or we can assert that 0 is less than or equal to 4.
Yeah. So
or 4 is greater than or equal to 0.
So table
that's
min.
That's fine to assert.
Table min must be less than or equal to our key max.
We can't always assert this. Then the next one will be even less, will be even smaller, right?
Yeah. Yeah.
Yeah, and so we don't need this. That's right. We don't need this condition then for greater than, actually. So yeah, we could go back to having separate loop conditions for the directions.
Okay.
That's actually one cheaper check, or one check cheaper.
Yeah, definitely.
In terms. Yeah.
Cool. And does it apply both ways, ascending as well?
I don't think so. Let's examine that carefully though in just a second. So we assert this is not equal to greater than, and then we compare. We can delete that part. Okay. Because here we compare. You can see the assert's different here. We're comparing key min with key min. We're doing the same thing. Well, like this is our query for descending. Let's say for the query for ascending, we're going from range 2 to 7. Okay, so then we're going to do our start iterator function. This will give us this table info because 2 is greater than 0 but less than 6. Then let's check our assert real quick. The assert says the key min of the table is less than or equal to our key min. 0 is less than or equal to 2, we're good.
And then we're going to hit an assertion failure on the next iteration.
Your key min is less than or equal to it.key min. That's fine. 6 is less. Oh, yeah, you're right.
Wow.
So we can't actually check that.
It's amazing how difficult this is. Like,
yeah. It's definitely a little bit humbling.
Yeah.
But we're making progress.
That's how I feel as well. Like the more I program, the slower I feel. Like I feel like it just gets harder and harder. And that's why I do more and more of these little notes, with these little
Yeah, I think we just try harder and harder stuff though as we program more.
That's probably it. Yeah.
Yeah, I definitely couldn't have done this a year ago, but we can make our way through it now.
Yeah. Yep. Yeah.
Cool. So this makes sense then. We always have the same two checks, except in this case we can lead this assertion. We can assert instead. We can lead the check essentially, because of the way our start iterator function works. We know that we'll never start out of bounds in that direction. Does that mean that our first item return is always valid when we're iterating in the descending direction? Is that right?
No, it isn't.
Let's figure out the case where that's not right.
Mm.
I think that's gonna be interesting for these asserts. So that could be a case when we have a thing that's not in our range at all. So the range 4 again. So 4 empty, and we're descending. So now we'll end up being returned this thing. Then we're going to compare keys, key min of the table to key max of our iterator range. So, and we're asserting that the key min is less than or equal to our key max. That passes.
Yeah.
And then we're going to check if the table key max is less than our key min, which it is. And so we then return null. So you're right. We don't always, the first thing is not always valid, but we handle that correctly with the current code.
Okay.
As we check this here. But it will always be valid on this end, is what we're saying, throughout the whole iteration.
Yeah. It seems that
this is correct now. I'm pretty confident.
Yeah. I just want, because it looks correct, because in the worst case we're going to crash, because we've got the symmetry there and we've got the assertion.
Yeah.
I just want to understand what we're saying. I guess it does make sense because we're descending. We're going from left to right. So key mins are always going to be decreasing. So
yeah. So I guess the question would be, why can't we assert this when we're ascending?
Yeah. I think maybe
because we don't have a key max, of course. Yeah.
Yeah. Maybe if we look at our example again and write it in a way that it fails the first time.
For ascending?
Yeah. So
we have that here. So yeah.
Okay.
And so we're going to end up getting this table returned. And so you'll then pass the key min it'll pass the first of these checks. Key max is greater than key min. That's comparing 0 to 4, or 0 to 4, this 4. But it's going to fail the second check. And the reason why we can't have the assert in this case is because we don't have table info.keyMax in our start iterator function.
Yeah.
But we do have table info.keyMin in our start iterator function. This is checking the start bound of the iteration. This one, after the first iteration, this will always return false, I believe. Is that right? Like if we manage to make one step and just say we were here, but we still have the key min of 4, then this will always return false, because the key, if the table info key max is greater than our, yeah. Yeah. It's tricky stuff. I think this is correct though.
Yeah, I'm happy that ascending is definitely correct, because we're checking the whole range of the table.
Yeah.
And then I just want to double check, like with some more examples in our notepad. Just some more, try and see if we can come up with a counter example, like just a bit different. Maybe we can copy and paste.
Try and make this assertion fail?
Yeah, see if we can do it. I'm happy that it's correct, but maybe I guess I could be a bit more. I'd like to understand it better. Maybe we can copy.
Yeah, we definitely need to write a comment there saying why we can assert this.
Yeah.
And so,
Yeah.
yeah,
Maybe
need
we.
people to explain it.
Yeah. Shall we copy and paste this assertion, just this assertion, into our notepad and then see what will make it fail? Because my short-term memory, I keep each time we switch, then I keep trying to remember now what are we checking? Are we going?
Let me write it also obviously. So we're
Yeah.
saying not equal to greater than. That means it's less than.
Or equal to.
So that's less than or equal to key max.
Yeah.
Equal info. I'm going to say table.keymin is less than or equal to if.keymax.
Yeah.
I'll put that at the top because that's the
Thanks.
most important thing we're doing right now.
Yeah.
All right. Now we've got everything loaded into our L1 cache and we're ready to go.
Thanks, Isaac. Cool. So for it to fail, keymin will have to be bigger than keymax. So we'll have to land up with
we
6.
can never hit that case because we always subtract 1 if we hit that. That's the same comparison we do when we're finding the place to start our search in start iterator.
Yeah. Yeah, because
we'll never actually return a table that hits that. Yeah.
Our binary search is going to return the smallest key that's greater than.
Yeah.
And then
so
if it's inexact, we're going to go 1 left still.
Yep. Exactly. And so that's what the other cert we used to have here was comparing keymin to keymin. And that was true for the first iteration, because that's also the comparison we're doing in start iterator, right? We're comparing the keymin we're searching for with the keymin in our index. We're ascending a direction. But the problem is that they would then fail for subsequent iterations.
Yeah.
In this case, though, we don't have the case where it fails for subsequent iterations, and that's why we can do this assert instead of putting it in a condition.
Yeah.
We could do like an assert if iteration count equals 1, then we could assert that this is this is false.
Yeah.
But we can't do that in general.
Yeah.
I think that makes sense to me now. Are you good?
Yeah, I'm good. Another way I was thinking also with that assert is we're saying that because we're going in descending order, we expect that the table info key min will always be less than or equal to our key max. And that's just because the tables are in sort order by key min. But on the other hand, they're not in sort order by key max. They're only in sort order by key min.
Well, they're not. They actually are in sort order by key max, since we skip overlapping tables.
Okay. Yeah. Okay.
I think the key realization is that it's the same comparison we use in our binary search in the start keys or start iterator function.
Yeah.
Yeah.
And it's the bias of our binary search that we're gonna get the greater thing. We could rebias our binary search to get the smaller thing.
Yeah, exactly. And then we could assert the other direction, I suppose.
Yeah.
But yeah.
Awesome.
Check. The same check. The same key comparison. Form in iterator start. Or not that one, just iterator start. Is that sufficient, do you think? Or is that going to confuse us when we come back to this?
I think it confuses me because in my mind I think iterator start is only what we do at the beginning, but will this hold true for every iteration around this loop? And
it does.
I'm just explaining if I come back to this later.
Yeah.
So I think the reason it holds true is because we're just simply going in descending order. So if we okay, I'm with you now. It's because iterator start and because it's actually in iterator start because that's where we do the binary search, and because the binary search has a bias to be on the greater side. That's why we know it's always going to be greater as we descend, because binary search sets us up to be on the right-hand side.
And since this remains true beyond the first, beyond the first
iteration.
Iteration.
Yeah.
Cool.
Nice.
In the other case, it would be we would be able to assert it, but it wouldn't remain true beyond the first iteration. That's the difference.
Yeah.
So I'm gonna add a comment here that says here we can't assert.
Yeah. If we were thinking we could assert, then it would be the assert would be on table key max versus key min. That would be where our assert would be.
Yeah.
And we can't. It would be that. And we can't because our index doesn't use key max at all. So it doesn't.
There's no guarantee on the first iteration that this is true.
Yeah.
We can't. It is not keyed that. That's perfect. That's why this doesn't work, because we don't have key max available in the indexes.
Yeah.
Awesome.
Yeah.
We've tied it all together now.
Yeah. Cool.
That table. This is beyond the first iteration. This is actually always true. As the key max of tables is as only the key min. Index.
Yeah.
In our keynotes.
Yeah.
Or root/keynotes.
Yeah. And then we should say, maybe we should say only the key min of a table is stored in our root keynotes to fix the...
Only the key min of...
a table. Or of each table is stored in our root keynotes.
It's not every table. Yeah. It is each table if we're talking about the keynotes as well.
Yeah.
We can say here that on subsequent iterations.
Cool.
Iterations. Here we go.
Nice.
I'm happy I understand it now.
Yeah, me too.
We've been able to explain it well and concisely in the comments, so we've got it now.
Shall we check on Monday when we come back to this if we're still good?
We definitely should.
Yeah.
We've also got this video now for us just talking about it for like half an hour that we can refer back to if we ever forget again.
Yeah. I spotted some things what we could do. Maybe we must just say only the key min of a table is stored in our root key nodes, so that we're not referring to necessarily all or each of a table. So the check will always be true. And then on the second, in the descending comment, where we say comparison, there's a I at the end. We must just drop.
Oh yeah. Comparison.
Yeah.
There we go.
And I don't know, Isaac, maybe where we say perform in iterator start, we could say is exactly the same key comparison we perform when doing binary search in iterator start. So we just link it back to that binary search bias.
Yeah.
This is great comment.
Okay, this line's kind of long. It's annoying me.
Yeah.
Like just. just think it'd be a little bit more neat if it was wrapped like this, I think.
Yeah.
Okay.
And then cool. Then I thought what we should do too is for our ascending branch, we should swap the two clauses around so that they mirror each other. So we could see the actual one we would have done the assert on. And then that curly we can bring up a line onto the is Zig format one? We can't bring that
That's
curly
Zig
up.
format style.
Okay, cool.
I think it's actually better like this too. Otherwise, it gets you get this where you then have the same indentation of these two lines.
Yeah.
Yeah. And so you can think that this first one's part of the loop. In C, I would do it like this. Like in some C style guides, that's what WL Roots uses, but this is also pretty good.
No, that's much better actually. Thanks for pointing that out. That's really cool. It makes so much sense like this. Yeah.
No problem.
So, Keyman.
A new line there, and then snapshot time, I guess.
Yeah. You know what? I've got to sign off because I've got to head to get back a little bit earlier. I've just got to grab something at the shops.
All right, no worries.
And maybe it's a good.
I guess we can just add this. Yeah, well, this will be a nice to-do to solve on Monday. I think it's pretty simple. Maybe we'll find something fun to do again, but I think check snapshot or continue is pretty simple.
Yeah, I'm hoping that maybe this will make it easy for level 0. Like.
Oh yeah, that's what we can talk about on Monday.
Yeah, cool. Yeah. So, but hey, Isaac, it's been an awesome first week back. It's been really nice.
For sure.
Yeah,
this has been really fun, getting back into this stuff, and I feel like we've actually gotten a lot done, a lot of tricky stuff.
Yeah, nice.
Cool.
Yeah, so I'm pretty chuffed too. We're just like chipping away, we're getting there, and this is much harder than consensus.
I don't know.
Yeah.
I haven't done the consensus really. You did all the consensus stuff, so I can't judge.
Yeah. It just feels harder and harder, you know. But this is
we don't have a paper telling us what to do anymore. We're making up a lot more by ourselves, just kind of figuring things out as we go.
Yeah.
So that makes it definitely harder.
Yeah. It feels to me too like
from a design perspective.
Yeah, definitely. It also feels like this couldn't be more optimal. Like I don't think it could be leaner. You know, I can't see another way.
It's pretty simple. Like how the data layout is pretty simple. The code is definitely not trivial, because I think that's more because we're making it fast though. We're like trying to not do unoptimal things.
Yeah.
It's definitely not easy. Let's leave it at that.
Let's leave it at that. Yeah, so have a great weekend.
You too.
Yeah, the Tiger Wheel sessions, Friday, 14th January, session 8. See you Monday.